3I/Atlas. More questions than answers documentary for sleep. The night sky is wide, and for most of human history, it has been both familiar and distant at the same time. People have looked upward and traced patterns, given names to constellations, and recorded the slow movement of stars across the seasons. For the most part, the heavens appear unchanging, calm, and predictable. A star that rises in the east tonight will do so again tomorrow, and the following night after that. Yet, every so often a faint visitor appears, a point of light that was not there before. It drifts slowly across the dark canvas, moving in ways that stars never do. Such objects are comets, asteroids, and, on rare occasions, something more unusual. In recent years, astronomers noticed an object called 3I/Atlas. Its name, long and somewhat technical, refers to its place in the quiet catalog of astronomical surveys. To most, it passed without fanfare. Yet to those who follow the patient record of the skies, it represented something unusual. It was not simply another comet, not simply another rock circling the sun, but something that seemed to have arrived from beyond. It is one of only a handful of interstellar visitors ever recorded by human eyes. This is not a story of dramatic discoveries or sudden revelations. Instead, it is a story told slowly, through careful measurements, faint photographs, and thoughtful reflection. It is about how astronomers noticed, recorded, and discussed this visitor. And it is about how, even in the quietest parts of the universe, questions remain unanswered. If this gentle journey through the silence of the stars helps you find a sense of calm, you are welcome to remain with us. These stories are not made to excite, but to quiet the mind, offering a steady rhythm of thought that can carry you toward rest. If you wish to hear more of these soft histories of the night, you may choose to follow along with the channel. By doing so, you will always have a quiet companion when you need it, waiting to fill the silence with slow and measured words. Explanation of naming conventions and how 3I/Atlas fits into them in astronomy. Names may appear complicated at first glance, yet each part of a name carries information. A long series of letters and numbers might look uninviting, but such precision allows astronomers across the world to know exactly what is being described without confusion. This system, which appears technical and distant, is built from the need to organize thousands upon thousands of objects in the sky, many of which are faint, temporary, or moving. The object we are speaking of is known as 3I/Atlas. The name is not chosen at random, nor is it intended to be memorable in a poetic sense. Instead, it follows rules established by astronomical bodies so that the designation itself reveals part of the story of its discovery. The 3I portion tells us that it is the third recognized interstellar object. Before it, two others had been formally accepted, 1I/Oumuamua and 2I/Borisov. The use of I signals that this is an interstellar visitor, meaning it did not originate within the solar system but appears to have entered from outside, on a path not bound to the sun. The numbering sequence begins with 1 and increases as new objects are confirmed, providing a quiet historical record in the name itself. The second part of the name, Atlas, refers to the survey that first detected it. ATLAS is an acronym for the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built primarily to watch for potentially hazardous near-Earth asteroids. By placing the survey's name into the designation, astronomers acknowledge the source of the discovery, linking the object forever to the instruments and project that revealed it. This practice of including discoverers' names or survey names is common in astronomy. Over time, the designation becomes both a label for scientific classification and a marker of human activity, showing the tools and people who happen to be watching at the right moment. The logic of such naming conventions stretches back through centuries of astronomical practice. When comets were first recorded in ancient chronicles, they were often described by the year of their appearance or by who observed them. In some traditions, they were linked to events on Earth, their names tied to omens or royal decrees. As astronomy became more formal, and as the number of known comets increased, this informal practice became difficult to manage. By the 17th and 18th centuries, astronomers began cataloging comets systematically, eventually leading to the designations we use today. In the 19th century, Comets were named after their discoverers, sometimes resulting in single objects carrying multiple names when discovered independently by observers in different locations. This was workable when only a handful of comets appeared each year. In the 20th and 21st centuries, when automated surveys began detecting dozens or even hundreds of comets annually, a more precise and standardized method was required. Today, the International Astronomical Union, or IAU, oversees the naming process. Newly discovered comets are first given provisional designations. These are temporary names that reflect the year and half-month of discovery, along with an alphabetical code indicating order. For example, a comet found in the first half of January might receive a designation beginning with the letter A, while one found later in the year would move further along the alphabet. Once the comet's orbit is determined and confirmed, a permanent designation is assigned, reflecting whether the object is periodic, non-periodic, or interstellar. Periodic comets, which return on predictable orbits, receive a P in their designation, along with a sequential number. Non-periodic comets, which pass once and do not return, receive a C. Interstellar objects, as a new category, have been marked with an I. This addition acknowledges the need to expand the system as new discoveries challenge existing categories. Thus, 3I/Atlas is not merely a string of letters and numbers. It is a quiet summary, the third object recognized as interstellar, found by the Atlas survey. Its name places it in a lineage with 1I/Oumuamua, discovered in 2017, and 2I/Borisov, discovered in 2019. By doing so, the name reflects the slow expansion of human awareness, each designation marking a rare moment when material from beyond the solar system happens to pass near enough to be noticed. The way names are structured in astronomy reflects a preference for order and continuity. Unlike mythological or dramatic titles, which may spark curiosity but fade with time, systematic designations remain stable. A catalog entry will mean the same thing in 100 years as it does today. Scientists rely on this stability. When they search for data or attempt to compare observations across decades, the consistency of naming conventions ensures that confusion is minimized. The detached, factual tone of these designations may appear lifeless, yet it is precisely this lack of embellishment that allows for clarity across cultures and languages. The designation also ensures that an object cannot be lost in the shuffle of human memory. Many comets appear faintly and then fade. Without careful cataloging, they could be rediscovered and mistaken for something new. By maintaining detailed records tied to systematic names, astronomers can cross-reference and confirm that what they are seeing has been recorded before. With interstellar objects, which pass through only once and never return, the need for precise identification is even greater. The name becomes the sole permanent marker of its fleeting presence, fixed in human records long after the object has disappeared from view. In the case of 3I/Atlas, the designation arrived quietly, like the object itself. It did not come with celebration or media attention at first. It entered the catalog as one entry among many, noted for its trajectory, its brightness, and its unusual speed. Only later did discussion grow, as astronomers recognized what the path implied. Yet the name, calm and factual, remained the same. It continues to remind us that even extraordinary objects are folded into the steady routine of astronomical record-keeping, their uniqueness hidden behind letters and numbers that look much like any other. The naming conventions of astronomy reveal something about the discipline itself. They suggest a culture of patience, of long timelines, and of a deliberate avoidance of unnecessary embellishment. Each name tells us not only what an object is, but also how the community of observers prefers to record the universe, with consistency, neutrality, and respect for the slow accumulation of knowledge. In this way, 3I/Atlas is both an astronomical object and a small symbol of how human beings choose to organize their understanding of the sky. The Atlas survey, history, design, and daily operation. The name Atlas refers to the Asteroid Terrestrial Impact Last Alert System. It is not a single telescope but a coordinated network, developed to provide humanity with early warnings of asteroids that might approach Earth. The system was conceived in the early 21st century as governments and research institutions recognized the practical value of monitoring the skies with greater regularity. While astronomy has always been a pursuit of curiosity, the purpose of ATLAS was straightforward and functional: to detect objects that might one day pose a hazard. ATLAS began with support from the University of Hawaii and funding from NASA's Planetary Defense Coordination Office. The project aimed to create a pair of small, wide-field telescopes rather than rely on one large instrument. This approach allowed each telescope to cover a broad swath of the sky quickly, trading detail for reach. With wide-angle optics and sensitive digital detectors, ATLAS could scan the visible sky several times per night, noticing faint points of light that had shifted position. The first telescope was established at Haleakala Observatory on the island of Maui. Its location, high above sea level, provided clearer skies and less atmospheric distortion. Soon after, a second telescope was installed on Mauna Loa, another high mountain in Hawaii. Together, these instruments formed the backbone of the survey, creating overlapping coverage that improved reliability. Over time, additional units were planned in other parts of the world, ensuring that cloudy weather or daylight in one region would not leave the sky unobserved. The design of ATLAS prioritized routine. Each night, the telescopes sweep across large sections of the sky in a prearranged pattern. Their cameras capture digital images at set intervals. Specialized software then compares these images to earlier frames, searching for differences. Stars remain fixed relative to one another, forming a reliable background. If a faint dot has shifted slightly between exposures, the software marks it for further inspection. This process runs automatically, handling more data in a single night than earlier astronomers could have processed in years. The daily operation of ATLAS reflects this balance of automation and human oversight. Each night, the telescopes gather their images. The computers analyze them in real time, flagging candidates. In the morning, astronomers review the flagged points, separating noise from genuine moving objects. Once a potential asteroid or comet is identified, its coordinates and brightness are sent to international databases, particularly the Minor Planet Center, which collects such reports from around the world. There, the new entry can be compared with existing records, checked against known objects, and either cataloged as a rediscovery or logged as something new. Because of its wide coverage, ATLAS does not focus on a single star or region. Its strength lies in the repetition of broad surveys. Night after night, it builds an ongoing record, noticing faint newcomers that might otherwise be overlooked. Most of what it finds are small asteroids that pass at safe distances, never threatening Earth. Yet each discovery, no matter how minor, contributes to the growing picture of near-Earth space. By filling in the details of this environment, ATLAS provides context for unusual finds, such as 3I/Atlas. The importance of such surveys lies not only in detection but in reassurance. By constantly watching, they confirm that the vast majority of objects pose no risk. This quiet monitoring is a form of planetary insurance, offering early warning in the unlikely event of a dangerous approach. The same instruments that protect Earth also add to the scientific record, noting faint comets, variable stars, and other transient events. In this way, ATLAS contributes not just to defense but to the broader study of the universe. The routine nature of its work makes ATLAS well-suited to discovering something like 3I/Atlas. Interstellar visitors do not announce themselves. They appear as faint moving points, indistinguishable from comets or asteroids at first glance. A survey that systematically covers the sky night after night increases the chance of noticing such a point. Once noticed, further observation can refine the orbit, revealing its unusual origin. Without such a program, an object passing quickly through the solar system might remain unseen, lost in the background of stars. On any given night, the telescopes of ATLAS operate without drama. They turn across the sky, collect light, and store images. The data flows quietly to computers, where software runs its checks. Human astronomers wake to review the results, marking what is worth forwarding. The system is designed not for spectacle but for consistency. Its true achievement is not in any single discovery but in the steady accumulation of small observations, each one another dot in the patient mapping of the heavens. In this sense, The discovery of 3I/Atlas reflects the system's quiet effectiveness. A visitor from interstellar space happened to drift across its field of view. The survey, doing what it does each night, noticed a faint shift, a movement against the stable backdrop. The data was logged, processed, and confirmed. There was no moment of sudden revelation, no dramatic pointing of telescopes in urgent pursuit. There was only the continuation of routine, and within that routine, the appearance of something rare. Atlas shows how modern astronomy relies less on individual observers at eyepieces and more on networks of machines that watch tirelessly. Where once a comet might be discovered by chance, noticed by a farmer or sailor glancing at the sky, today it is more likely to be detected by automated surveys comparing millions of pixels across thousands of images. This shift has changed the texture of discovery. It has become less about moments of wonder and more about steady maintenance, the quiet scanning of space for changes. Through Atlas, one can see how science has become both more powerful and more procedural. The ability to detect interstellar objects is remarkable, yet the process feels ordinary, folded into nightly routines. This ordinariness is part of its strength. By treating each night as another chance to gather consistent data, the survey ensures that rare events do not pass unnoticed. It is within such ordinary patterns that extraordinary things are sometimes revealed. The history, design, and daily operation of Atlas remind us that great discoveries often arise not from grand gestures, but from persistent watchfulness. By maintaining its rhythm, the survey builds a record that captures both the common and the rare. 3I/Atlas, named for this system, is a reminder that the vastness of space can be observed through quiet, repetitive work. The name links the visitor not only to its interstellar origin but also to the instruments and routines that brought it into human awareness. The distinction between asteroids, comets, and interstellar objects in the quiet practice of astronomy classification is essential. The sky is filled with countless moving bodies, and without categories, it would be difficult to describe what is being observed. Among these bodies, three groups often overlap in public discussion: asteroids, comets, and interstellar objects. Each has its own definition, and each carries a set of characteristics that set it apart. The lines between them can sometimes blur, but careful observation allows astronomers to distinguish one from another. Asteroids are perhaps the simplest to describe. They are rocky bodies, composed mostly of metals and silicate minerals. They are fragments left over from the formation of the solar system, orbiting the sun much as planets do, but on smaller scales. Most asteroids are found in the asteroid belt between Mars and Jupiter, where millions of objects circle in relatively stable paths. Their sizes vary greatly, from pieces no larger than a pebble to bodies several hundred kilometers across. Asteroids do not usually display tails or comas. They appear as points of light, moving slowly against the stars, their nature revealed only by study of their orbits and reflected sunlight. Comets, by contrast, are composed largely of ice mixed with dust. Their nuclei are solid, but when they approach the sun, heat causes the ice to sublimate. Gas and dust escape, forming a glowing coma around the nucleus and sometimes a tail that extends for millions of kilometers. The tail always points away from the sun, shaped by solar wind and radiation. This activity makes comets more visually striking, though most are faint. Historically, comets drew much attention because they appeared suddenly and changed in appearance as they moved across the sky. Yet in essence, a comet is an icy body whose behavior depends on distance from the sun. Far away, it remains inert, much like an asteroid. Near the sun, it transforms into something more dynamic. The line between asteroids and comets is not always strict. Some objects, known as active asteroids, display comet-like activity under certain conditions, though they are primarily rocky. Others are cometary in origin but no longer show activity, their volatile material long since exhausted. For this reason, astronomers sometimes speak of a continuum rather than two separate classes. Still, the distinction remains useful. Asteroids are generally rocky and inactive, while comets are icy and active when warmed. Interstellar objects form a newer category, one that challenges older divisions. They are defined not by composition or activity but by trajectory. An interstellar object is one whose orbit cannot be bound to the Sun. Its speed and path indicate that it came from outside the solar system and will not remain within it. Such objects move on hyperbolic orbits, curving past the Sun once before continuing outward into interstellar space. They may appear asteroid-like or comet-like, depending on what they are made of, but what sets them apart is origin. They are visitors rather than residents. The first interstellar object formally recognized was 1I/Oumuamua in 2017. Its motion made clear that it was not native to the solar system. The second was 2I/Borisov in 2019, which behaved like a typical comet but with an orbit showing interstellar origin. 3I/Atlas, the subject of this account, became the third. Each entry confirmed that the solar system is not isolated but open to material drifting between stars. These objects are rare in observation, not because they are rare in space, but because they are small, faint, and move quickly relative to Earth. The distinction between interstellar objects and ordinary asteroids or comets lies mostly in the mathematics of orbit calculation. When astronomers measure the position of a moving body night after night, they can plot its path relative to the Sun. If the orbit is elliptical, the object is bound, meaning it will remain within the solar system, repeating its path. If the orbit is parabolic or hyperbolic with enough velocity to escape, the object is unbound. For an interstellar object, the orbit is hyperbolic with a velocity higher than the solar system can account for. Such speeds cannot be explained by gravitational nudges from planets alone. They indicate an origin beyond the solar neighborhood. The practical process of distinguishing among these categories is methodical. First, the object is observed. Its brightness, motion, and apparent size are measured. Second, the data is compared with known catalogs. If it does not match a known asteroid or comet, it is tracked further. Third, its orbital parameters are calculated, requiring several nights of measurement. If the orbit remains uncertain, astronomers continue observing until confidence improves. Only then can they assign the object to one of the established categories. In the case of 3I/Atlas, early observations placed it within the category of a comet, due to a faint surrounding haze that suggested sublimation. Yet the orbit revealed something more. Its trajectory indicated a hyperbolic path, one that had not originated from the outer solar system but instead entered from beyond. Thus, the designation combined both aspects, a cometary body and an interstellar orbit. It was catalogued as 3I/Atlas, bridging the familiar categories of comet and interstellar object. The distinctions are useful not because they capture every detail, but because they allow communication. When astronomers refer to an asteroid, they convey a general picture, rocky, inert, orbiting the Sun. When they refer to a comet, they suggest an icy body with the potential for activity. When they refer to an interstellar object, they highlight the unusual fact of an origin outside the solar system. Each term provides a shorthand, a way of placing an object within the broader map of the sky. Over time, these distinctions may change. As more interstellar objects are discovered, subcategories may emerge. Some may appear asteroid-like, others comet-like, others difficult to classify. Already, astronomers debate whether new terms are needed, or whether the existing framework can be stretched. The history of astronomy shows that categories evolve as new phenomena are observed. Yet, in the present, the triad of asteroid, comet, and interstellar object remains sufficient to describe what is seen. In this way, classification becomes part of the quiet rhythm of astronomy. Each new discovery is sorted, named, and recorded, joining countless others in databases that grow year by year. The distinctions are not dramatic, but they provide order. Within that order, unusual cases such as 3I/Atlas stand out, not because their names are poetic, but because their designations do not fit the ordinary patterns. They remind us that the sky is larger than the categories we use, and that sometimes, what appears faint and simple carries a story of vast distance and quiet motion across the stars. How astronomers first noticed 3I/Atlas. The discovery of 3I/Atlas did not arrive with sudden excitement or dramatic announcement. Instead, it emerged gradually, through the quiet routine of nightly observations conducted by the Atlas survey. Each night, the telescopes of the system scanned wide fields of the sky, capturing thousands of images, each filled with countless points of light. Among those points, some represented stars fixed in place, while others shifted slowly. These shifting points were of interest, for they might indicate comets, asteroids, or less common visitors. In late 2019 and early 2020, Atlas, operating as usual, recorded one such faint point. At first, it was indistinguishable from the many small objects the system regularly detects. The raw data appeared as a pixel-sized spot, visible only when compared across multiple frames. The automated software noted the change, marking the position for human review. This process, repeated nightly, was designed to catch small moving bodies long before they attracted broader attention. Astronomers reviewing the data noticed the faint object had shifted relative to the star field in a way that suggested genuine motion. Once identified, its position was reported to the Minor Planet Center, where new discoveries are catalogued. At that stage, little was known. Its brightness was measured, its coordinates recorded, and its motion tracked over a short interval. The object was logged as another comet candidate, with provisional identification. Like many discoveries, it entered the database quietly, one among thousands of similar entries. In the following days, astronomers returned to the object, gathering more data. With each additional observation, its path became clearer. The movement suggested it was not simply drifting within the solar system but following a trajectory unusual enough to warrant further analysis. At first, the differences were subtle. Its apparent speed, its changing brightness, and the angles of its motion all hinted at something more than a routine comet. But such hints required confirmation, and so the monitoring continued. The early period of discovery was characterized by repetition rather than revelation. Each night, the telescopes recorded more images. Each morning, the data was processed and reviewed. Each report added another line to the growing record of measurements. From these lines, astronomers began to construct an orbit step by step. Calculating an orbit is not immediate. It requires multiple points of reference spread across time. With 3 observations, a rough estimate can be made, but it is imprecise. With 10 or 20, the path becomes more certain. With each new set of data, the orbit of this faint object sharpened into view. As this process unfolded, astronomers outside the Atlas project also began to contribute. Once a potential new comet is announced, other observatories around the world often attempt to confirm the sighting. Using their own instruments, they take images and measure positions, adding data to the collective pool. This collaborative approach ensures that the discovery is not based on a single instrument or location. Weather, technical errors, or local conditions can influence results, so independent confirmation is essential. With 3i/Atlas, this confirmation arrived steadily, with observers in different countries submitting measurements that aligned with the initial reports. Gradually, the orbit calculations revealed something unexpected. Instead of the closed, elliptical path of a comet belonging to the solar system, the trajectory appeared hyperbolic. This meant the object was not bound to the sun. It had entered from outside and would leave again, never to return. This realization unfolded slowly, as the data accumulated and confidence in the calculations increased. It was not a moment of sudden revelation but a gradual recognition, drawn from the patient work of many. During this early phase, the object also displayed characteristics typical of a comet. A faint coma surrounded its nucleus, evidence that sublimation was taking place. Gas and dust were escaping, giving it the diffuse appearance common to comets when they approach the sun. The combination of a cometary appearance with a hyperbolic orbit was striking, for it suggested that this was not merely an asteroid-like body passing through but an active comet that had traveled across interstellar space. Despite the significance of this finding, the tone of the reports remained steady and factual. The Minor Planet Center circulated updates with measured language, noting the unusual orbit and the cometary features. Scientific papers began to be drafted, but they too used the cautious phrasing of astronomy, emphasizing what was observed, what was calculated, and what remained uncertain. In this way, the early discovery of 3I/Atlas mirrored the object itself. Quiet, unassuming, and marked by gradual recognition rather than sudden drama. For astronomers involved in the observation, the process was familiar. Many had followed similar steps with countless other comets and asteroids. The object was unusual, but the method of discovery was the same. Nightly scans, automated detection, human review, cataloging, confirmation, and calculation. It was through this rhythm of repeated observation that the significance emerged. What seemed at first like another routine discovery became, through patient analysis, the third recorded interstellar object. The discovery also highlighted the value of surveys like Atlas. Without constant monitoring, such a faint and fast-moving object might have been missed. Interstellar visitors do not linger. They pass quickly through the solar system, visible only for a short window. By watching night after night, the survey increased the chance of noticing one in time to study it. The detection of 3I/Atlas demonstrated that even rare events can be caught by ordinary routines, provided those routines are consistent. In the broader picture of astronomy, the discovery of 3I/Atlas was another entry in the steady log of observations. It did not disrupt the nightly schedules of observatories. It did not cause immediate changes in practice. It was simply recorded, studied, and added to the growing catalog of known objects. Yet within that quiet process lay something extraordinary. Evidence of material that had traveled from another star system, drifting silently until it intersected with human awareness. Thus, the first noticing of 3I/Atlas can be described not as a single event but as a sequence of small steps. A faint point on a digital image. A flag in automated software. A confirmation by human review. A provisional entry in a database. A growing set of orbital calculations. A slow recognition of interstellar origin. Each step was modest, but together they formed the path by which the object was discovered. In this way, the discovery reflects the character of modern astronomy itself. It is a discipline of patience, built on repetition, supported by collaboration, and expressed in cautious language. The significance of 3I/Atlas lay not in sudden excitement but in the quiet accumulation of evidence. Through this process, astronomers first noticed the object, recognized its uniqueness, and placed it within the orderly system of naming and classification. What began as a faint moving point became 3I/Atlas, a record of interstellar motion preserved in human observation. The slow unfolding of early observations and confirmations once the faint moving point that would become known as 3I/Atlas was first recorded, the process of confirmation began. This process is rarely swift. It depends on repetition, on careful comparison, and on the gradual building of certainty through observation. In astronomy, no discovery is accepted until enough independent evidence supports it. For that reason, the earliest weeks of tracking 3I/Atlas unfolded quietly, step by step, in much the same way as countless other objects before it. Each night added new data points. The telescopes of Atlas, as well as other observatories around the world, continued to measure its position against the background of stars. These measurements were precise, down to fractions of an arcsecond, yet taken individually they did not reveal much. The meaning emerged only when they were combined, forming a chain of positions that mapped the object's path across the sky. The longer the chain grew, the more confident astronomers became in the orbit they were calculating. In those early days, the data was shared quickly and openly. The Minor Planet Center collected reports from multiple observatories and published them for the scientific community. Amateurs with access to modest telescopes also contributed, their images confirming the object's position. The collaborative nature of astronomy meant that no single observer carried the burden of proof. Instead, confirmation was distributed, spread across continents and instruments, each adding another piece to the emerging picture. Gradually, the object's hyperbolic orbit became clear. At first, there was uncertainty. Was this simply a comet from the distant Oort cloud, flung onto an unusual trajectory by gravitational influences? Or was it truly interstellar, with a velocity too high to be explained by interactions within the solar system? With each new measurement, the calculations refine themselves, reducing error margins and narrowing possibilities. The conclusion settled slowly but firmly. The orbit was not bound. The object had entered from beyond the solar system. The early observations also confirmed its cometary nature. Photographs showed a diffuse coma, faint but unmistakable, surrounding the nucleus. Spectroscopic data, where available, indicated gas and dust emission consistent with known comets. In this way, 3I/Atlas aligned with expectations of what an interstellar comet might look like, providing a useful contrast with 1I/Oumuamua, which had appeared more asteroid-like and raised debates about its composition. The presence of a coma removed some ambiguity, situating 3I/Atlas more firmly within the comet category while still marking it as unusual for its origin. The pace of confirmation was deliberate. In science, especially in astronomy, haste can lead to errors that spread quickly. For that reason, even as the data accumulated, official reports retained cautious wording. Phrases such as provisional orbit, possible interstellar origin, and preliminary classification were used. This restraint is characteristic of the field, where confidence is earned through patient repetition rather than bold statements. Only after weeks of consistent observation did the designation 3I/Atlas become widely accepted, signaling the third interstellar object formally recognized. The slow unfolding of confirmation also reflected the rhythms of the sky itself. Weather sometimes prevented observation. Clouds, storms, or poor atmospheric conditions interrupted the sequence, leaving gaps in the record. When skies cleared, observations resumed, filling in the missing points. This natural variability reinforced the need for collaboration, as observatories in different parts of the world could continue monitoring when others were obstructed. Through this global network, the continuity of data was maintained, despite local interruptions. As confirmation spread, astronomers began preparing analyses. Papers were drafted, describing the object's orbit, brightness, and behavior. These papers circulated within the community, subject to peer review and cautious scrutiny. The language remained measured, avoiding speculation and focusing on what could be directly observed. The object's interstellar origin was treated as a significant but natural extension of known science, not as something extraordinary. In this way, the early scientific response mirrored the quiet tone of the observations themselves. For those following closely, the process may have seemed uneventful. Each update resembled the last. Another set of measurements, another refinement of the orbit, another confirmation of the coma. Yet this monotony was not a flaw but a feature. It ensured that the discovery was built on solid ground, leaving little room for doubt. By the time the designation was fully accepted, the foundation of evidence was broad and reliable. In hindsight, the unfolding of 3I/Atlas appears inevitable. From first detection to full confirmation, the sequence followed established patterns. Automated surveys detect faint points. Astronomers review them. The Minor Planet Center collects and shares the data. Observers worldwide contribute, filling in gaps. Orbits are calculated, refined, and tested. Once confidence reaches a sufficient level, a designation is assigned. This process, repeated countless times for comets and asteroids, carried the discovery of 3I/Atlas along its quiet path. What distinguished this object was not the process but the outcome. The same routine that had catalogued thousands of ordinary comets now revealed one from beyond the solar system. The discovery did not alter the rhythm, but it gave the routine a new significance. It showed that even the most extraordinary visitors can be noticed through ordinary means, provided those means are applied consistently. The early confirmations also revealed the limits of observation. Despite careful measurement, much remained unknown. The exact size of the nucleus could not be determined, hidden behind its coma. The composition could only be inferred indirectly. Its point of origin within interstellar space remained a mystery, beyond the reach of current instruments. These uncertainties were accepted as part of the discovery, reminders that astronomy often leaves questions open. The role of observers was not to resolve every detail but to record what could be known with care and accuracy. By the time the discovery entered wider awareness, the unfolding of observations had already established its place. The designation 3I/Atlas was secure. The orbit was confirmed as interstellar. The object was noted as cometary in nature. The essential facts were settled, even if many details remained uncertain. What began as a faint point on a digital image had become a recognized entry in the catalog of human knowledge, preserved not by sudden insight but by steady confirmation. The story of its early observations is therefore less about drama and more about process. It is about how many small acts of attention, distributed across nights and observatories, accumulate into certainty. It is about how science proceeds not in leaps but in steps, each one adding to the last. And it is about how something as vast as interstellar travel can be revealed through something as modest as a shifting pixel on a screen. In this way, the slow unfolding of 3I/Atlas mirrors the nature of the universe itself. Vast processes play out over immense timescales, unnoticed until they intersect briefly with human awareness. Our recognition of them depends on patience, repetition, and the willingness to accept that certainty takes time. The discovery of 3I/Atlas was no exception. It was not sudden, not dramatic, but slow and deliberate, confirmed piece by piece until its presence became undeniable. What interstellar means in astronomical language, the word interstellar, is built from two parts. Inter, meaning between, and stellar, meaning related to stars. In its simplest sense, interstellar refers to the space that lies between the stars. This is not empty space in the absolute sense, though it may appear so when viewed with the unaided eye. Instead, it is a vast region filled with faint gas, scattered dust, and the occasional fragment of solid material drifting slowly through the galaxy. In astronomy, the term is used carefully to distinguish what belongs to a single star system from what exists outside of it. For most of history, people assumed that the space between stars was empty. When early telescopes revealed more stars, their light still appeared to shine through a dark background. It was only in the 20th century, as spectroscopy improved, that astronomers began to detect traces of material in this darkness. They saw faint absorption lines in the spectra of distant stars, indicating the presence of gas along the line of sight. These lines revealed that the so-called void between stars contained hydrogen, helium, and small amounts of other elements. This mixture became known as the interstellar medium. The interstellar medium is extremely thin by human standards. A cubic centimeter of air at sea level on Earth contains roughly 10 billion molecules. By contrast, a cubic centimeter of interstellar space may contain only 1 or 2 atoms. Yet across the immense distances between stars, even such sparse material accumulates. Clouds of gas stretch for light years, shaping the galaxy in ways that influence the formation of stars and planets. Dust grains, small and faint, scatter starlight, producing subtle patterns of dimming and reddening. These details are almost invisible to the human eye but become clear through careful measurement. When astronomers use the term interstellar object, they mean a solid body, such as a comet or asteroid, that originated outside the solar system and now passes through it. Its orbit shows that it is not bound to the sun but merely visiting, crossing our region of space before moving on. Such objects are distinguished from those that formed within the solar system, which are bound by the sun's gravity. The definition is based not on appearance but on motion. If an object travels too fast to be captured by the sun, and its trajectory indicates an origin beyond, it is considered interstellar. This usage connects the concept of interstellar space to tangible objects. The interstellar medium is mostly gas and dust, too faint to see directly. But occasionally, larger fragments, once part of distant planetary systems, are ejected and drift between stars. When one of these happens to cross Earth's vicinity, it becomes visible to telescopes. These encounters are rare, but they provide the most direct way to study material from outside the solar system. Rather than interpreting faint absorption lines, astronomers can observe a cometary nucleus, measure its behavior, and compare it with familiar solar system bodies. The meaning of interstellar also carries an implication of distance. The nearest star system, Alpha Centauri, lies over 4 light-years away. A light-year is nearly 10 trillion kilometers. At such scales, even the fastest spacecraft launched from Earth would take tens of thousands of years to reach another star. Material that crosses from one system to another therefore travels for immense periods of time. An interstellar object like 3I/Atlas may have spent millions, even billions, of years drifting before entering our view. To call it interstellar is to acknowledge this deep history, most of which will remain unknown. In the language of astronomy, interstellar does not imply anything mysterious or extraordinary. It simply describes origin and trajectory. A comet with an interstellar orbit is not treated as fundamentally different in composition from one formed in the solar system, unless observations suggest otherwise. The term places the object in context, noting that it did not belong here originally but happens to pass through. By using precise terminology, astronomers avoid speculation. They prefer to describe what is measurable: the orbit, the speed, the path across the sky. Yet for listeners and readers outside astronomy, the word interstellar often carries a sense of wonder. It evokes the idea of distances beyond comprehension, of journeys between suns. It suggests a scale so large that human time becomes insignificant. This contrast between technical use and popular imagination is common in astronomy. The language is designed to be neutral, but the concepts themselves can feel vast and overwhelming. In the calm practice of observation, however, interstellar is a category, not a mystery. It is a way to mark what comes from beyond, to place such objects within the larger map of the galaxy. Thus, when astronomers named 3I/Atlas, the I did not imply drama. It simply indicated that the orbit could not be bound to the sun, that the object had entered from interstellar space. The designation recorded this fact in the same way a catalog entry might record brightness or position. The word interstellar in this context was an instruction. This object is to be filed among those that drifted from outside. Behind the calm language lies the immensity of its journey, but in the records it is presented with the same neutrality as any other comet or asteroid. In this way, the meaning of interstellar in astronomy reflects the discipline's character. It is precise, cautious, and restrained. It acknowledges what can be measured and avoids what cannot. It places the extraordinary within ordinary frameworks, showing that even something that has traveled across light years can be described in the same language used for more familiar objects. To understand interstellar is not to be swept into speculation but to see how astronomers fit rare visitors into their patient catalog of the sky. The vast distances between stars, measured in light years. When astronomers speak of interstellar space, they are speaking of distances so large that ordinary measures such as kilometers or miles become impractical. To describe such scales, a unit known as the light year is used. A light year is the distance that light travels in 1 year, moving at nearly 300,000 kilometers per second. Over the course of 12 months, that speed carries light about 9.5 trillion kilometers. This figure is beyond ordinary human experience, so the light year serves as a more manageable way of expressing the separation between stars. The nearest star system to Earth is Alpha Centauri, lying just over 4 light-years away. In numerical terms, this means that the light reaching us tonight from Alpha Centauri left its source more than 4 years ago. When we observe it, we are observing the past. This distance, though short in cosmic terms, is immense compared with anything within the solar system. To travel from Earth to the Moon requires about 1.5 seconds for light. To reach the Sun requires about 8 minutes. To cross to Alpha Centauri requires more than 4 years. The scale expands rapidly, moving from minutes to years, as soon as one steps beyond the solar system. Beyond Alpha Centauri lie other stars, each farther still. Sirius, the brightest star in the night sky, is about 8.5 light-years away. Vega, well known from summer skies, is about 25 light-years away. Deneb, a luminous star forming part of the Summer Triangle, lies nearly 2,600 light-years away. At such distances, light that began its journey before human history is only now arriving. The night sky, filled with stars, is thus also filled with timescales, each point of light representing a different era in the distant past. For objects like 3I/Atlas, which arrive from interstellar space, these distances are part of their history. Such objects are believed to be fragments ejected from the formation of planetary systems around other stars. When planets grow within disks of gas and dust, gravitational interactions may cast smaller bodies outward. Some fall inward to their stars. Others are flung outward, gaining enough velocity to escape entirely. Once free, they drift between stars, moving slowly relative to galactic scales but swiftly compared with human measures. A single fragment may take millions of years to cross the space between one star and the next. The distances ensure that encounters are rare. Even though countless fragments are thought to drift through the galaxy, they are spread thinly across its immense volume. The chances of one passing near enough to be detected within a human lifetime are small. The discovery of 3 interstellar objects in recent years, Oumuamua, Borisov, and Atlas, suggests that many more must exist, unseen, but the vast separations between stars mean that each detected case remains unusual. The rarity is not because the objects are few, but because the distances they traverse are vast. These distances also highlight the scale of the Milky Way itself. The galaxy stretches over 100,000 light-years across. From our position within it, light from the far side would take 100 millennia to reach us. Stars orbit its center in slow paths that take hundreds of millions of years to complete. Against such a backdrop, a fragment like 3I/Atlas is a small traveler, yet its journey across light-years places it within the same scale as the galaxy's great structures. It is a reminder that even the smallest bodies move within an immense framework of space and time. The use of light-years as a unit offers clarity but does not diminish the challenge of comprehension. 9.5 trillion kilometers is difficult to imagine, and 4 times that is equally difficult. Instead of picturing numbers, it is often easier to consider relative comparisons. Light from the Sun reaches Pluto in just over 5 hours. That same light would require more than 4 years to reach Alpha Centauri. If Earth were scaled down to the size of a grain of sand, Alpha Centauri would still be many kilometers away. The distances grow larger with each comparison, emphasizing the gulf between stars. When astronomers study interstellar objects, they do so with the knowledge that these distances shaped their journey. The velocity needed to cross from one star system to another reflects the scale of separation. Once ejected, an object drifts with steady momentum, covering fractions of a light-year per 100,000 years. Over spans that dwarf human history, such bodies accumulate distance, until at last they cross into another system's reach. To detect one is to glimpse a traveler that has been in motion since long before our species began. The concept of light years also reinforces the finite speed of information. Nothing, according to current understanding, can exceed the speed of light. That limit sets the pace at which the universe can be known. The farther away something is, the older the information we receive. To look outward is to look backward in time. A comet arriving from interstellar space carries with it not only the dust and ice of its composition but also the record of a journey across ages. The light year as a measure captures both distance and duration, reminding us that the two are inseparable on cosmic scales. In this sense, the vast distances between stars are not empty stretches but parts of the fabric of the universe. They define the movement of objects, the limits of communication, and the rhythm of discovery. For an interstellar comet such as 3I/Atlas, those distances are the stage upon which its path was traced, long before it came near enough to be seen. Its passage into the solar system was brief, but the journey that brought it here spanned light years, measured not in days or centuries but in epochs beyond human measure. Thus, when we say that 3I/Atlas is interstellar, we acknowledge not only its trajectory but the scale of space it has crossed. Between stars lies separation measured in trillions of kilometers, or in years of light. That separation ensures rarity, but it also ensures continuity. Objects that drift between stars carry traces of their origins across the galaxy, linking distant systems through slow exchange. The distances are immense, but they are not barriers. They are simply the quiet spaces through which matter drifts, unhurried, over the course of cosmic time. The history of thinking about material drifting between stars. The idea that material might travel between stars is not new, though its history is one of gradual development rather than sudden realization. In the earliest traditions of astronomy, the heavens were often imagined as fixed and unchanging. Stars appeared constant, moving only in predictable patterns across the night sky. Comets, when they appeared, were thought to belong to Earth's atmosphere or to be temporary lights placed in the sky as omens. The concept that solid objects might drift freely between stars was far from consideration. In ancient Greece, philosophers debated the nature of celestial bodies. Some, such as Aristotle, held that the heavens were made of a special, incorruptible substance, different from earthly matter. In this framework, stars and planets were part of a perfect sphere, isolated from change and decay. Such a view left little room for the idea of wandering fragments crossing interstellar space. Others, however, such as the atomists, imagined a universe filled with countless particles moving in infinite space. Though they had no means of observation, their philosophy suggested that material might travel endlessly, perhaps even between distant suns. Through the Middle Ages, astronomical thought was dominated by geocentric models, where Earth stood at the center and celestial spheres carried stars and planets in fixed arrangements. The notion of objects drifting between stars was unnecessary within such models, for the stars themselves were believed to be attached to a distant sphere, unmoving and eternal. Only with the gradual shift to heliocentric ideas, advanced by Copernicus in the 16th century and expanded by Galileo and Kepler, did the heavens begin to be understood as dynamic, with planets and comets moving according to natural laws. By the 17th century, comets were recognized as celestial objects traveling through space rather than atmospheric phenomena. Isaac Newton, in his Principia Mathematica, described their orbits as conic sections, showing that some could be parabolic or even hyperbolic. This recognition introduced the possibility that a comet might not return but instead pass through once and continue outward indefinitely. While Newton's examples were based on solar system comets, his mathematics allowed for the theoretical existence of bodies that arrived from beyond. In this way, the idea of interstellar visitors began to take shape, though evidence remained absent. In the 19th century, as telescopes improved and more comets were catalogued, astronomers began to wonder about their origins. Some speculated that the Oort cloud, a vast reservoir of icy bodies surrounding the solar system, supplied comets at long intervals. Others considered whether some comets might enter from interstellar space. The concept was difficult to test, since determining a comet's orbit required precise observations, and even small errors could make an orbit appear hyperbolic when it was not. Most supposed interstellar comets were eventually reclassified as belonging to the solar system once more data was gathered. Still, the notion persisted that the stars did not exist in complete isolation but exchanged matter slowly over time. In the 20th century, with advances in astrophysics, the idea of interstellar drift became more firmly grounded. Studies of star formation revealed that young planetary systems eject large numbers of small bodies as they settle into stable configurations. Simulations showed that many of these bodies achieve escape velocity, leaving their parent systems entirely. Once ejected, they enter the broader galaxy, drifting as interstellar objects. Theoretical estimates suggested that the galaxy should be filled with such fragments, though their density remained too low for frequent detection. The belief that interstellar material must pass through the solar system from time to time became increasingly accepted, even if direct observation remained elusive. The discovery of meteoritic material on Earth also encouraged speculation. Some researchers suggested that certain unusual meteorites might have originated outside the solar system, delivered by chance after long journeys. While most meteorites can be explained as fragments of asteroids or comets native to our system, the possibility of interstellar origins was occasionally raised, though without conclusive evidence. The notion tied into broader discussions about panspermia, the hypothesis that life might spread between stars via drifting material. Though controversial, these discussions highlighted how interstellar exchange was becoming a part of scientific imagination. By the late 20th and early 21st centuries, the expectation of detecting an interstellar object grew stronger. Automated surveys were beginning to monitor the sky with unprecedented detail. Models predicted that sooner or later, one of these surveys would notice an object on a clearly hyperbolic trajectory. The only question was when. In 2017, the discovery of 1I/Oumuamua confirmed the long-held prediction. 2 years later, 2I/Borisov provided further confirmation. By the time 3I/Atlas appeared, the history of speculation had prepared astronomers to accept it as part of an emerging category rather than a surprise. Looking back, the history of thought on drifting interstellar material shows a progression from denial to speculation to expectation, and finally to confirmation. Ancient astronomers saw the heavens as fixed. Early modern thinkers introduced mathematical frameworks that allowed for escape and drift. 19th century observers speculated cautiously, while 20th century astrophysicists predicted a galaxy filled with wandering fragments. In the 21st century, technology allowed those predictions to be tested and confirmed. The significance of this history lies not in sudden shifts but in the slow adjustment of human understanding. Ideas about interstellar material did not emerge all at once. They unfolded gradually, shaped by observation, mathematics, and theory. The discovery of 3I/Atlas was therefore not the start of a new idea but the continuation of a long line of thought, stretching back through centuries of speculation. Its passage through the solar system provided direct evidence of what had long been imagined, that stars do not remain isolated, but exchange matter across the immense distances of the galaxy. Why interstellar comets are so rarely observed. The passage of 3I/Atlas through the solar system was unusual not because such objects are thought to be rare in the galaxy, but because noticing one is difficult. Interstellar comets are expected to exist in enormous numbers, drifting quietly between stars. Yet they are seldom observed, and only in recent years have a handful been detected with certainty. The reasons for this rarity lie not in their scarcity alone, but in a combination of factors: size, brightness, speed, and the limitations of observation. Most interstellar comets are small. When planets form around young stars, countless icy bodies are created in the process. Gravitational interactions scatter many of them outward. Some collide, some remain in distant orbits, and some are cast completely free of the system. The ones that escape are usually fragments smaller than planets, smaller even than large asteroids. Their nuclei may measure only a few kilometers across, sometimes less. Against the vast backdrop of space, such small bodies are almost invisible until they come very near another star. Brightness is another factor. Comets shine only by reflecting sunlight and, in some cases, by releasing gas and dust that reflect and scatter light. In interstellar space, far from any star, they are completely dark. Only when they enter a stellar system and approach close enough for light to illuminate them do they become visible. Even then, they may remain faint, requiring sensitive telescopes to detect. By the time they brighten enough to be noticed, they are often already passing through and soon moving away again. Speed also plays a role. An interstellar comet typically travels at tens of kilometers per second relative to the Sun. This velocity is enough to carry it across the solar system in a matter of months. Unlike periodic comets, which circle the Sun repeatedly and can be tracked over many years, interstellar comets appear briefly and then vanish. Their short windows of visibility limit opportunities for study. An observatory may detect one only after it has already passed its closest approach, leaving little time to gather data. The limitations of observation further explain the rarity. Until recently, the sky was not monitored continuously with wide-field digital surveys. Observatories focused on specific targets or small regions, missing faint moving points outside their chosen fields. Only with the development of automated surveys like Pan-STARRS, Catalina, and Atlas has the coverage become broad enough to increase the likelihood of detection. Even so, the surveys must sift through millions of stars each night, searching for faint movements that may represent comets. Many candidates prove to be ordinary asteroids. The challenge is not only detecting interstellar comets but recognizing them before they fade from view. Historical limitations meant that earlier interstellar visitors may have gone completely unnoticed. Before the era of digital detectors, comets were discovered visually or on photographic plates. Observers scanned the skies with telescopes, often guided by charts and experience. While effective for bright comets, this method could not reliably capture faint, fast-moving objects. It is likely that many interstellar comets passed through unnoticed in past centuries, their presence unrecorded simply because no one was looking in the right place at the right time. The geometry of approach also influences visibility. A comet passing close to Earth is easier to detect than one moving on a path far from the inner solar system. Many interstellar comets may cross the outskirts, never coming near enough to be bright enough for observation. Their trajectories carry them silently through the outer reaches, invisible even to large telescopes. Only those that chance to pass within range of sunlight strong enough to trigger visible activity can be discovered. Even when conditions are favorable, classification is not immediate. A newly discovered comet may appear to have a hyperbolic orbit, suggesting interstellar origin, but further observations often adjust the orbit back into a closed path, showing that it belongs to the solar system after all. Distinguishing true interstellar comets from long-period comets requires time and careful calculation. Many candidates fail this test, and only a few remain confirmed. This process of elimination further reduces the number recognized as interstellar. The rarity of observation also reflects the immensity of the galaxy. With stars spread light-years apart, the density of drifting objects is low. Even if billions exist across the Milky Way, the volume is so vast that their presence at any given point remains thin. For Earth to encounter one is an uncommon event. The fact that 3 have been identified in recent years may reflect improved technology rather than an actual increase in encounters. As surveys become more sensitive, more will likely be noticed, but they will remain exceptional compared with the routine discovery of solar system comets and asteroids. For scientists, this rarity is both a challenge and a motivation. Each interstellar comet provides unique information, but opportunities to study them are few. Instruments must be directed quickly, and measurements gathered efficiently, before the object fades. The quiet urgency of these efforts reflects the awareness that another such opportunity may not come soon. Yet the calm language of reports conceals this urgency, focusing instead on the steady accumulation of data. The rarity of interstellar comets does not change the method of study, only the value placed on each observation. In summary, interstellar comets are rarely observed because they are small, faint, fast, and often distant. The history of limited observational technology further reduced their chances of being noticed. Only with modern surveys has detection become more likely, though still uncommon. The discovery of 3I/Atlas represents one success among countless missed opportunities, a reminder that the galaxy holds more than we can see, and that most interstellar visitors pass silently through without our awareness. The rarity itself contributes to the calm wonder of such discoveries. To know that a faint point of light represents a traveler from another star system is to glimpse the vastness of the galaxy in a tangible form. Yet the fact that so few are seen emphasizes the limitations of human observation, reminding us that we witness only fragments of the broader cosmic exchange. The infrequency does not mean absence, but rather underlines the scale of space and the quiet difficulty of perception. Quiet speculation on how many may exist unseen if only 3 interstellar objects have been detected so far, Oumuamua, Borisov, and Atlas. It is natural to wonder how many others must exist beyond our sight. Astronomers approach this question not through imagination but through careful estimation, built from models of planetary formation and simulations of stellar systems. These models suggest that what has been observed represents only a fraction, the visible tip of a much larger distribution drifting unseen across the galaxy. When stars form, they are surrounded by disks of gas and dust. Within these disks, particles collide and clump together, forming larger bodies that eventually grow into planets, moons, and smaller fragments. The process is turbulent. Gravitational interactions between growing planets scatter many of the smaller bodies outward. Some remain bound on distant orbits, forming reservoirs like the Oort cloud around our own Sunday. Others gain enough velocity to escape entirely. Once free, they no longer belong to any one star system but instead wander the spaces between, slowly drifting along the galaxy's rotation. Simulations of this process suggest that each planetary system may eject trillions of small bodies during its formation. Multiplied by the number of stars in the galaxy, over 100 billion, the total number of interstellar fragments becomes vast beyond easy comprehension. Most will never come close enough to be detected from Earth, but the sheer quantity implies that countless unseen objects pass silently through interstellar space at all times. Estimating how many might pass near the solar system requires further calculation. Astronomers combine known detection rates with the sensitivity of surveys to extrapolate an unseen population. From the detection of Oumuamua in 2017 and Borisov in 2019, models were adjusted to suggest that interstellar objects may be common visitors, perhaps entering the inner solar system every few years. Yet because most are small and faint, only a few reach the threshold of visibility. Many more may pass undetected through the outer solar system, too distant or dim to register. The existence of such an unseen population changes how astronomers think about the galaxy. It suggests that stars are not isolated but exchange material continuously, though slowly. Over billions of years, fragments from countless systems may drift and intermingle, forming a shared galactic background of comets and asteroids. This exchange is quiet, not dramatic, but steady, reminding us that isolation in space is relative. Even across light years, the slow trade of matter continues. For Earth, this means that interstellar objects are not rare in absolute terms but rare in detection. A visitor like 3I/Atlas is unusual to us only because our instruments notice so few. Beyond the reach of telescopes, many others likely pass by, dark and unremarked. Some may be as small as boulders, invisible against the stars. Others may be larger but follow paths that never bring them near the sun, leaving them in permanent obscurity. The unseen population is therefore not a single set of bodies but a spectrum of sizes, speeds, and compositions, spread across galactic space. Speculation about their number must remain cautious. Observations are few, and the uncertainties are large. Estimates vary widely, depending on assumptions about planetary system formation and ejection rates. Some models suggest that for every star in the galaxy, billions of interstellar objects exist. Others propose even larger numbers, stretching into the quadrillions. These figures are difficult to imagine, but they emphasize that what has been observed so far is not the whole story, only the portion visible to present-day technology. The thought of so many unseen objects invites further reflection. Each fragment carries within it the history of another system. Some may contain ices from stars very different from our own. Others may be rocky pieces, shaped by collisions in distant planetary disks. Together, they form a kind of archive scattered across the galaxy, though almost entirely inaccessible. To observe even one like 3I/Atlas is to receive a sample from beyond, a messenger of processes that occurred far away and long ago. The unseen majority continue their journeys unnoticed, but they share the same origin: the restless formation of stars and planets across cosmic time. For those who study astronomy, the unseen population represents both a mystery and a certainty. It is mysterious because so little can be known directly, yet certain because theory demands its existence. The few detections already made confirm that such objects are real. The rarity of observation does not imply scarcity but difficulty. With more sensitive instruments, such as those expected from future surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time, more may be detected. Over decades, the unseen population may become less invisible, as technology slowly catches up with expectation. Still, even as detection improves, most interstellar objects will remain forever unobserved. The galaxy is too large and the fragments too small. The majority will continue their silent drift, never approaching close enough to be illuminated by a star, never reflecting enough light to be noticed. Their presence is part of the background, not of observation but of probability. They are reminders that what is seen is always a fraction of what exists. In thinking about how many interstellar comets may exist unseen, the tone of astronomy remains measured. Rather than speculate beyond evidence, astronomers present ranges, models, and cautious language. They recognize the limits of knowledge while acknowledging the inevitability of abundance. The unseen population is not a matter of belief but of expectation, grounded in the physics of planetary systems and the mathematics of galactic distribution. It is understood not with certainty of detail but with confidence of principle. Thus, the story of 3I/Atlas, like those of Oumuamua and Borisov, points toward something larger. These few visible visitors hint at an unseen multitude, passing silently across light years, unnoticed but real. To imagine their number is to imagine the galaxy itself, filled not only with stars and planets but with fragments, small and quiet, drifting endlessly between. The vast majority will never be observed, yet their existence forms part of the structure of space, shaping the slow exchange of matter across the Milky Way. The discovery of Oumuamua in October of 2017, astronomers operating the Pan-STARRS survey in Hawaii noticed a faint moving point of light that did not match known catalogued objects. At first, it appeared to be another asteroid or comet, of the kind routinely recorded in the survey's nightly images. Its brightness was modest, and its movement across the sky was unremarkable in the short term. The discovery was reported to the Minor Planet Center, which logged it with a provisional designation, as is standard procedure for new objects. In the beginning, there was no sense that this body would prove unusual. It was simply another entry in the steady accumulation of celestial measurements. As additional observations were gathered over the following nights, the path of the object became clearer. Astronomers calculated its orbit, refining the data with each new measurement. Slowly, it became apparent that its trajectory could not be explained as an ordinary ellipse around the Sun. The orbital elements indicated a hyperbolic path, meaning the object was not bound by the Sun's gravity but would pass through the solar system only once before continuing outward. This was significant, for it implied that the object had entered from interstellar space. The Minor Planet Center confirmed the trajectory and formally designated the object 1I/2017 U1. The 1I marked it as the first recognized interstellar body, while 2017 U1 reflected the year and half-month of discovery. Soon afterward, the name Oumuamua was chosen, a Hawaiian term meaning a messenger from afar arriving first. The name acknowledged both its origin beyond the solar system and the location of its discovery in Hawaii. The designation and name together established its place in astronomical history as the first confirmed interstellar object. The discovery of Oumuamua highlighted the effectiveness of wide-field surveys. Pan-STARRS, like Atlas, was designed to scan large portions of the sky systematically, searching for moving objects. Its instruments collected digital images that could be compared night after night, revealing faint shifts. Without such surveys, an object as small and faint as Oumuamua might have passed unnoticed. It was detected not because it was bright but because the routine of observation caught it within its brief period of visibility. In terms of physical appearance, Oumuamua presented challenges. It was too small and distant to be resolved into a clear shape by telescopes. Instead, astronomers relied on its light curve, the variation in brightness as it rotated. The light curve suggested that it was elongated, perhaps cigar-shaped or flattened like a pancake, with a length several times greater than its width. As it rotated, the amount of reflected sunlight changed dramatically, producing sharp variations in brightness. This was unusual compared with most known asteroids, which tend to be more compact. Despite these peculiarities, the discovery was treated with the same calm procedures as any other. Observations were coordinated across observatories worldwide, additional data was collected, and reports were shared through established channels. The orbit was refined, the brightness recorded, and the light curve analyzed. Scientific papers were written, using the cautious phrasing typical of astronomy. The object was unusual, its shape uncertain, its origin interstellar. Each fact was presented with precision, leaving room for future correction. Oumuamua did not display a coma or tail, the features commonly associated with comets. This absence led to initial classification as an asteroid-like body. Yet its slight acceleration, measured over weeks, suggested non-gravitational forces, possibly from outgassing too faint to be detected directly. This ambiguity left astronomers cautious. Was it a rocky asteroid with unusual properties, or a comet with activity too subtle for current instruments? The question remained unresolved, but the tone of discussion stayed neutral, focusing on observations rather than speculation. The timeline of visibility was short. Oumuamua moved swiftly through the solar system, becoming fainter as it receded from the sun. Within weeks, it had passed beyond the reach of most telescopes. The opportunity to study it in detail was brief, and by the time its significance was fully appreciated, it was already fading. The fleeting nature of the encounter emphasized the importance of constant monitoring. Only through continuous surveys could such rare visitors be noticed in time to record them. For astronomers, the discovery of Oumuamua was not a surprise in principle. Theoretical models had long predicted that interstellar fragments must exist. What was surprising was that one had finally been observed. The detection confirmed expectations, showing that the galaxy does indeed send occasional travelers into the solar system. It also provided a new category for astronomical records: interstellar objects, marked with the I designation. From a historical perspective, the discovery marked the transition from speculation to observation. For centuries, astronomers had debated whether interstellar comets might exist. With Oumuamua, the question was no longer hypothetical. The object itself served as direct evidence. Its hyperbolic orbit required no extraordinary explanation. It was simply a natural fragment, likely ejected from a distant planetary system, passing through as predicted. Its presence validated decades of theoretical work, placing interstellar material firmly within the realm of observation. The calm unfolding of Oumuamua's discovery reflects the character of modern astronomy. There was no moment of sudden revelation, no dramatic turning point. Instead, there was a sequence of small steps: detection by a survey, reporting to a central database, confirmation by multiple observatories, calculation of an orbit, assignment of a designation, and recognition of its uniqueness. Each step followed established routines, and together they revealed something extraordinary within the ordinary. Though its details remain uncertain, Oumuamua's discovery demonstrated that interstellar visitors can be noticed and recorded. It showed that the galaxy is not closed, that fragments drift between stars and occasionally cross our path. Its brief appearance set the stage for future detections, including Borisov and Atlas, confirming that interstellar material is not only real but observable. The first interstellar object, therefore, was not a singular event but the beginning of a new chapter in astronomy, one written in the same steady, careful style as all that came before. The shape, spin, and brightness variations of Oumuamua after initial observations confirmed the interstellar trajectory of Oumuamua. Astronomers focused on understanding its physical characteristics. Direct imaging was impossible, as the object was distant and small. Instead, researchers relied on photometry, measuring variations in brightness as the object rotated. The light curve, a graph of brightness over time, revealed unusual behavior. Over its short observational window, the object's brightness varied dramatically, suggesting an elongated form. Estimates indicated that its length might be several times its width, though exact measurements were uncertain. These calculations were made using standard models of light reflection and rotation, applied in a methodical, step-by-step manner. Rotation periods were derived from these brightness variations. Oumuamua appeared to complete a full rotation in a few hours. As it spun, different surface areas reflected sunlight toward Earth, producing predictable increases and decreases in observed light. The degree of variation implied a highly elongated or flattened shape. Such forms are rare among solar system asteroids but are not physically impossible. The light curve analysis relied on repeated observations from multiple telescopes, each adding incremental precision. Data points were combined to produce a consistent estimate of rotational behavior, and error margins were carefully noted in scientific publications. Surface properties were inferred from color measurements. Observations in different wavelengths indicated a relatively neutral to slightly reddish hue. The color was similar to some known solar system objects, particularly outer solar system bodies. Researchers compared Oumuamua's spectral properties to known asteroids and comets to identify similarities. The comparison showed no extreme anomalies. It suggested that the object had undergone space weathering, the slow alteration of surface materials by cosmic radiation and micrometeorite impacts. These processes occur over millions of years and affect both composition and reflectivity. Shape and rotation data together prompted models of possible geometries. The elongated interpretation was consistent with the large range in brightness, assuming uniform surface reflectivity. Alternative models included flattened shapes with irregular features. In all cases, the conclusions were cautious, emphasizing that observational limitations imposed significant uncertainty. Astronomers avoided definitive statements about exact shape, using probabilistic language instead. The tone of publications remained neutral, reporting calculations without dramatizing the unusual proportions. The absence of a visible coma or tail was noted in every observation. Typical comets display gas and dust emissions when heated by the sun, creating visible halos. Oumuamua did not show such features. This led to early classification as an asteroid-like object. However, subtle non-gravitational accelerations were later detected in its motion. These accelerations suggested weak outgassing, insufficient to produce a detectable coma, yet sufficient to slightly alter trajectory. The discrepancy required careful measurement and repeated validation, conducted through standard astrometric procedures. The findings were reported with appropriate caution, emphasizing the data rather than speculation. The orientation of rotation was also studied. Researchers modeled possible spin axes to determine whether it was tumbling or spinning about a single axis. Evidence suggested a complex rotation, known as non-principal axis rotation. In such cases, an object wobbles as it spins, causing the light curve to be less uniform. Modeling this behavior involved solving equations of motion for rigid bodies under solar gravity, a standard technique in celestial mechanics. Results were consistent with the observed brightness variations and allowed astronomers to refine estimates of shape and size. Observations were limited by time and distance. As Oumuamua moved away from the Sun and Earth, it became progressively fainter. Data collected over a few weeks represented the maximum resolution achievable with current ground-based instruments. Astronomers acknowledged that many details would remain uncertain. The brief encounter exemplified the challenges of interstellar detection. Objects are fast, faint, and visible for only a short period. Methodical recording and careful analysis were essential to capture the available information. Comparison with solar system objects provided context. While elongated asteroids exist, Oumuamua's ratio of length to width was greater than typical. Its rotation was within observed ranges for small bodies, though somewhat more rapid. Surface color matched expectations for outer solar system material. The combination of traits was unusual but not unprecedented, reinforcing the importance of measured, neutral reporting. Rather than sensationalizing the differences, astronomers placed them within a framework of known celestial behavior. The analysis of Oumuamua's physical properties illustrated the interplay between observation, measurement, and modeling. Each step built upon prior knowledge. Telescopes recorded light, photometry extracted quantitative data, rotation and shape models interpreted variations, and comparisons with known objects provided context. Throughout, scientific rigor was maintained. Conclusions were drawn carefully, framed with appropriate uncertainty. The presentation of data remained calm and factual, suitable for methodical comprehension. By the end of the observational period, Oumuamua had passed beyond detection limits for most instruments. The light curve, spectral measurements, and rotational modeling were complete, forming a detailed but unexciting portrait of an interstellar object. Its elongated form, subtle color, rapid rotation, and faint acceleration were catalogued. While the object would never be observed again, the collected data provided a baseline for future interstellar detections. Researchers documented every measurement systematically, ensuring that Oumuamua passage could inform both current understanding and preparation for subsequent discoveries. In conclusion, the study of Oumuamua's shape, spin, and brightness was marked by methodical procedures, careful interpretation, and neutral presentation. There was no dramatic revelation or sudden discovery. Each insight emerged gradually, through repeated observation and calculation. The resulting description emphasized precision and calm clarity. Oumuamua's passage introduced a new category of objects, yet the manner in which it was studied remained consistent with centuries of astronomical practice. Its characteristics were unusual in combination, but each element fit within a framework of careful, neutral examination. Oumuamua's trajectory and hyperbolic orbit. Once Oumuamua's physical characteristics were sufficiently catalogued, attention turned to its trajectory through space. Calculating the path of any celestial object requires careful application of the laws of motion, gravitational influences, and precise positional measurements. Observatories around the world contributed data, each reporting the object's position at specific times. These measurements, taken over several weeks, allowed astronomers to determine the orbital elements, its path through the solar system, speed, and direction relative to the Sun and planets. The orbit was immediately recognized as hyperbolic. Unlike the elliptical orbits typical of solar system comets and asteroids, a hyperbolic orbit indicated that Oumuamua was not bound to the Sun. Its velocity exceeded the escape speed necessary to remain in orbit. In practical terms, this meant that the object had entered the solar system from interstellar space and would eventually leave, continuing its journey through the galaxy. Calculating hyperbolic elements involved determining parameters such as eccentricity, semi-major axis, and inclination. These calculations were performed using established techniques in celestial mechanics, each step verified to minimize error. Astronomers noted the direction from which Oumuamua had arrived. Its inbound trajectory was consistent with paths that might originate from nearby stellar neighborhoods, though the exact origin remained undetermined. Determining the source star or region requires knowledge of stellar motions, galactic dynamics, and assumptions about interstellar object ejection mechanisms. While the object's path provided clues, no definitive source could be identified. The data were reported systematically, emphasizing distances, angles, and velocities without speculating on origin stories or narrative interpretations. The hyperbolic nature of the orbit also implied that Oumuamua's speed increased as it approached the Sun and decreased as it moved away, according to the conservation of energy and gravitational principles. Precise measurements confirmed that its motion adhered closely to expectations based on Newtonian mechanics. Small deviations in speed were observed, later attributed to weak, asymmetric forces consistent with low-level outgassing. These non-gravitational effects were minor, yet detectable. Researchers applied standard orbital adjustment methods to account for them, maintaining a neutral, stepwise analysis. Inclination was another key parameter. Oumuamua's orbital plane differed significantly from the plane in which most solar system planets orbit, known as the ecliptic. Its path was tilted relative to planetary orbits, indicating a trajectory largely independent of the gravitational influence of planets. This observation reinforced its classification as an interstellar visitor. Inclination calculations were straightforward but required repeated observations to confirm precision. Each new measurement refined earlier estimates, contributing to a reliable depiction of the trajectory. The timing of perihelion, the closest approach to the Sun, was calculated next. Oumuamua passed relatively near the Sun, though not within planetary orbits. Determining perihelion involved combining positional data with orbital modeling. Observers noted the timing and distance carefully, as such information is essential for understanding solar heating effects, potential sublimation, and observational visibility. The calculations were routine yet methodical, performed with a calm precision suitable for documentation rather than dramatic presentation. Throughout its passage, Oumuamua remained visible for only a short period. Its increasing distance and decreasing brightness limited observation time. Each observatory's contribution was carefully logged, including times of observation, instruments used, and observational conditions. This meticulous record-keeping ensured that all trajectory calculations could be verified and reproduced by other researchers. Standard error analysis accompanied every reported parameter, maintaining scientific rigor and neutrality. Comparisons were made to known solar system objects with similar hyperbolic or near-parabolic orbits. While most comets with hyperbolic-like paths are influenced by planetary perturbations, Oumuamua's velocity exceeded what could be explained by solar system interactions alone. Its trajectory fit theoretical expectations for interstellar objects, confirming its unique classification. These comparisons were conducted with careful statistical treatment, avoiding narrative embellishment. The trajectory also informed predictions for future positions. Calculating the expected path required modeling the sun's gravitational influence and accounting for minor non-gravitational accelerations. These calculations demonstrated that Oumuamua would leave the solar system entirely, continuing indefinitely through the galaxy. Astronomers recorded projected positions at intervals, providing a reference for archival data. While the object would not be observable again, its passage offered a template for analyzing future interstellar objects. Finally, the combination of trajectory, hyperbolic orbit, and slight accelerations provided insights into the physical processes at work. Subtle forces consistent with weak outgassing were incorporated into models. Researchers emphasized that these effects were small and consistent with known physical principles, maintaining a neutral tone. There was no attempt to dramatize or speculate. Instead, the data were presented as carefully measured, stepwise phenomena. By the end of the observational campaign, Oumuamua's hyperbolic orbit was precisely defined. Astronomers had mapped its path with accuracy, documented its approach, perihelion, and exit trajectory, and noted minor deviations consistent with physical processes. The story of Oumuamua's movement through space was not one of excitement or drama but of methodical, patient observation. Its passage was recorded in the same careful, stepwise manner as countless other celestial objects, with the added note that it was the first known interstellar visitor, a subtle but remarkable milestone for astronomy. Oumuamua's faint outgassing and subtle anomalies. Observations of Oumuamua during its passage revealed subtle anomalies that prompted careful analysis. While the object did not display a visible coma, the small variations in its trajectory suggested that it experienced non-gravitational forces. These forces were attributed to a form of outgassing, similar to that observed in comets, though markedly weaker. Astronomers approached this discovery with precision, recording measurements, uncertainties, and time intervals, maintaining a neutral and methodical tone. Outgassing occurs when volatile materials near an object's surface sublimate due to solar heating. In the case of Oumuamua, calculations suggested that even minimal sublimation could produce the observed deviations from a purely gravitational orbit. Researchers applied standard models to estimate the magnitude of this effect. They accounted for factors such as solar distance, orientation, and rotation, observing that the forces involved were small yet detectable. Each adjustment to orbital models was documented carefully, allowing for replication by other teams. The shape and surface composition of Oumuamua also played a role. Its elongated form implied that even modest outgassing could produce directional acceleration. Small jets of gas, emanating from localized areas, would create gentle thrust along the object's spin axis. Observers recorded rotation rates, light curve variations, and inferred shapes, combining these data to produce a coherent, stepwise picture. At no point was speculation inserted. Instead, all interpretations were firmly grounded in observed, measurable phenomena. Astronomers noted that the lack of a visible coma or tail was not unusual for interstellar objects. The sparse environment and high velocity meant that any sublimation would be dispersed rapidly. Standard observational techniques were applied to confirm the absence of significant dust or gas clouds surrounding the object. Filters, exposure times, and photometric measurements were reported, ensuring that conclusions were transparent and verifiable. Minor accelerations were then incorporated into trajectory models. These adjustments improved the match between predicted and observed positions over time. Researchers described these corrections in formal, numerical terms, presenting data such as velocity increments, angular adjustments, and residuals. The process was meticulous, emphasizing the slow, deliberate refinement of knowledge rather than sensational interpretation. Comparisons were made with solar system comets experiencing low-level outgassing. While typical comets often display prominent comas, the phenomenon observed in Oumuamua was consistent with very weak sublimation. Astronomers treated these comparisons carefully, noting similarities and differences without dramatizing the object's uniqueness. The subtlety of the forces involved reinforced the impression of a gentle, measured process. Spectroscopic observations were conducted to search for volatile compounds. Weak emissions of certain molecules were suggested, though data remained inconclusive. Analysts reported flux measurements, wavelength calibrations, and signal-to-noise ratios, providing a neutral account of what could and could not be determined. The absence of strong spectral signatures did not negate the presence of minor outgassing. It merely confirmed that any emission was faint and dispersed. Rotation played a further role in the observed anomalies. Oumuamua's spin rate and axis orientation affected how forces were applied over time. Astronomers modeled rotational dynamics alongside sublimation effects, producing adjusted orbital predictions that matched observed positions. Each step in the modeling process was documented methodically, with care taken to describe assumptions, parameter values, and error margins. The subtle nature of these anomalies also offered insight into interstellar object dynamics. The low-level outgassing and minor accelerations were consistent with physical principles, confirming that Oumuamua behaved in ways expected of a small, icy, or volatile-rich object passing through a stellar environment. No extraordinary or unusual mechanisms were necessary to explain the observations. Researchers emphasized that the object's behavior was entirely within the range of known physics, reinforcing a calm and factual narrative. By the conclusion of the observational period, Oumuamua's trajectory, shape, rotation, and faint outgassing had been thoroughly analyzed. All adjustments were incorporated into predictive models, providing a clear, stepwise account of its passage through the solar system. The combination of careful measurement, methodical calculation, and neutral reporting produced a comprehensive, low-stimulation understanding of the object. This approach allowed astronomers to document a remarkable interstellar visitor while maintaining a sense of quiet order and clarity. The story of Oumuamua's subtle forces and gentle anomalies exemplifies the patient, meticulous work of astronomy. Observers recorded each detail, refined their models, and compared findings with known celestial behavior. Every calculation, measurement, and adjustment was undertaken in a calm, deliberate manner, emphasizing observation over speculation and documentation over drama. In this way, Oumuamua's passage became a record of careful, methodical study, preserving its significance while fostering a sense of tranquil, measured understanding. Oumuamua's departure and archival significance as Oumuamua continued its journey, moving away from the sun and receding beyond the planets. Observations gradually became more challenging. Its increasing distance reduced brightness, and telescopes required longer exposure times to detect the faint light reflected from its surface. Astronomers carefully recorded these measurements, noting changes in apparent magnitude, angular position, and the precision of each observation. Despite these challenges, every piece of data contributed to a coherent, stepwise understanding of its trajectory. The departure of Oumuamua was tracked systematically. Teams around the world coordinated observations, using established networks of telescopes and cameras. Data were shared, calibrated, and combined, producing a continuous record that spanned days, weeks, and months. The object's increasing velocity relative to the solar system was calculated from these measurements, using established physical principles and standard orbital mechanics. Each velocity increment, angle of approach, and deviation from predicted positions was documented carefully. Astronomers placed great importance on archiving this data. Observations of Oumuamua provided an unprecedented record of an interstellar visitor, offering insight into the physical properties, dynamics, and interactions of objects originating beyond the solar system. Archival records included raw images, calibrated measurements, spectroscopic data, and photometric analyses. Every file was cataloged systematically, ensuring future researchers could reference the information with clarity and precision. The archival significance extended beyond immediate scientific interest. Oumuamua's passage represented an opportunity to refine methods of detecting, tracking, and analyzing small, fast-moving objects. Techniques used for photometry, spectroscopy, and orbit modeling were applied consistently, with careful notation of assumptions, uncertainties, and correction factors. Lessons learned from this process informed future observational strategies, providing a reference framework for similar events. Long-term records also allowed for retrospective analysis. Years or decades later, astronomers could revisit the data, reapplying models with improved computational tools or refined physical assumptions. The archival nature of the observations ensured that Oumuamua's passage would remain a resource for study and comparison, preserving its place in the history of interstellar exploration. Observational patience was a defining feature of this period. As brightness decreased and visibility diminished, teams continued to monitor the object at regular intervals, following standardized protocols. Each session provided incremental data, contributing to a slow, cumulative understanding rather than dramatic revelations. The careful pace exemplified the methodical nature of astronomical research, emphasizing consistency, continuity, and attention to detail. The object's departure also offered an opportunity to study the interstellar environment. Measurements of trajectory, acceleration, and possible outgassing informed models of forces acting outside the solar system. Researchers considered the sparse interstellar medium, radiation pressure, and gravitational influences from distant stars, documenting each factor with precision. These analyses reinforced the view that Oumuamua's journey was governed by familiar physical laws, even across vast distances. In addition to its scientific value, Oumuamua's departure highlighted the collaborative nature of astronomy. Observatories across continents contributed observations, and coordinated efforts ensured redundancy and verification. Every step was recorded with a focus on clarity, reproducibility, and minimal interpretation, aligning with the calm, neutral tone appropriate for a sleep-inducing narrative. The final calculations of Oumuamua's orbit established its hyperbolic trajectory, confirming that it would not return to the solar system. Researchers documented the precise parameters of its path, including eccentricity, inclination, and asymptotic velocity. These measurements were integrated into catalogs of interstellar objects, creating a reference point for future encounters. The meticulous attention to detail ensured that the data could be used for comparative studies, simulation, and historical record. Archival significance extended to public databases and scientific literature. Observational records, analyses, and findings were submitted to astronomical journals and repositories. Each entry was accompanied by detailed methodology, tables of measurements, and uncertainty assessments. This systematic approach ensured that Oumuamua's passage would be accessible to both contemporary and future researchers, maintaining a permanent record of an interstellar event without embellishment or dramatization. As the object receded further, visual detection became increasingly difficult, yet the significance of the observations remained. The cumulative record provided a quiet testament to the thoroughness of modern astronomy. Each measurement, correction, and calculation contributed to a body of knowledge that could be revisited, refined, and extended, preserving the scientific value of the encounter. The story of Oumuamua's departure exemplifies a deliberate, measured approach to understanding a rare celestial visitor. Every observation was taken with care, every measurement recorded with precision, and every analysis conducted with methodological rigor. The passage from approach to departure, documented across multiple observatories and instruments, forms a complete, continuous record. This record embodies the patient, observational nature of astronomy, emphasizing process over drama, detail over speculation, and continuity over sudden revelation. By the conclusion of its monitored passage, Oumuamua had become both a subject of scientific study and a symbol of interstellar exploration. The combination of careful observation, systematic documentation, and archival preservation ensures that its journey will remain a resource for decades to come. Researchers can return to the data, reanalyze it with new models, and incorporate it into broader studies of interstellar objects. In this way, the passage of Oumuamua provides a lasting contribution to the measured, deliberate practice of astronomy, preserving calm insight within an ever-expanding cosmic context. Observing 3I/Atlas, early telescopic measurements after the announcement of 3I/Atlas's discovery, astronomers around the world began careful, systematic observations. Unlike dramatic stories of sudden cometary appearances, the initial work focused on methodical measurement, determining position, brightness, and motion with precision. Telescopes of varying sizes were employed, from small survey instruments to larger professional observatories. Each instrument had specific strengths. Wide-field telescopes allowed for repeated tracking over several nights, ensuring consistent positional data, while high-resolution instruments captured subtle changes in brightness and structure. Observations were conducted under controlled conditions. Atmospheric clarity, instrument calibration, and exposure times were recorded meticulously. Even minor variations, such as slight changes in ambient temperature or humidity, were noted because they could influence the apparent brightness or position of the object. Data were logged systematically, forming tables that included date, time, coordinates, apparent magnitude, and observational conditions. These records created a reliable baseline for understanding the object's motion through space. Photometric measurements were central to the early study of 3I/Atlas. Astronomers used multiple filters to assess the reflected light across different wavelengths. By measuring how brightness varied with color, researchers could infer information about surface composition. Although the results did not immediately reveal dramatic characteristics, the steady accumulation of data provided a slow, unfolding picture of the object. Variations were analyzed with care, avoiding assumptions beyond what the measurements directly indicated. Astrometric precision was equally important. Repeated positional measurements allowed the calculation of a trajectory, including speed, direction, and expected path through the solar system. Computational models incorporated gravitational influences from the Sun and planets, refining the predicted orbit over time. Each adjustment to the model was documented, ensuring that the process remained transparent and reproducible. This meticulous approach emphasized accuracy and reliability, rather than rapid or sensational conclusions. The gradual approach to observing 3I/Atlas reflects the patient nature of astronomy. Each night's observations added incremental clarity, allowing astronomers to track the object's movement with precision. Observers coordinated across time zones, ensuring continuity of data as the object shifted through the sky. This coordination created an almost continuous record, with overlapping measurements that could be cross-verified for consistency. Surface properties were examined indirectly. Light curves, representing brightness variations over time, were analyzed to estimate shape, rotation, and reflectivity. Even slight fluctuations were noted and documented, forming a detailed, quantitative picture of the object. Researchers were careful to distinguish between real physical variations and artifacts caused by instruments or atmospheric conditions, maintaining a neutral and objective record. Telescope technology played a subtle but critical role. Charge-coupled devices, computer-controlled tracking systems, and image stacking techniques all contributed to the accuracy of measurements. Observers took care to calibrate instruments before and after sessions, ensuring that measurements could be compared across different observatories. This consistency allowed for aggregation of data, strengthening confidence in the calculated trajectory and physical properties. Over the course of several weeks, patterns emerged. While no immediate visual features stood out, the accumulated photometric and astrometric data revealed a consistent path, confirming the interstellar nature of 3I/Atlas. Calculations indicated that the object's trajectory was hyperbolic, meaning it would not return to the solar system. The significance of this was noted without emphasis on drama. It was a fact derived from careful measurement and computation. Communication among astronomers followed established protocols. Observatories shared nightly results via secure channels, submitting data to centralized repositories. Each entry included timestamps, calibration notes, and observational conditions. This practice ensured that every measurement could be verified independently and incorporated into broader analyses. Archival records created a permanent, systematic account of the object's early observations. By the end of this initial period, 3I/Atlas had been observed with consistent precision, its path mapped, and its basic physical characteristics assessed. The slow accumulation of data exemplified the deliberate, careful approach required to study interstellar objects. Observations proceeded without urgency, emphasizing consistency, clarity, and reproducibility over sensational interpretation. Each night of measurement added incremental understanding, forming a comprehensive record that would support further study as the object moved away from the inner solar system. Tracking motion, calculating trajectory and velocity following the initial detection and early measurements, astronomers concentrated on tracking the motion of 3I/Atlas with precision. The process relied on repeated observations from multiple observatories across the globe. Each site provided positional data relative to distant stars, allowing the object's path to be triangulated with remarkable accuracy. Observers measured right ascension and declination, recording each night's position and comparing it with predictions from existing orbital models. The gradual refinement of these models reflected the patient nature of scientific inquiry, a steady accumulation of small, verifiable improvements. Velocity calculations were central to determining whether 3I/Atlas was a bound object of the solar system or an interstellar visitor. Using the observed positions over time, astronomers applied Newtonian mechanics, taking into account gravitational influences from the Sun and major planets. Slight discrepancies between observed and predicted positions prompted further examination, leading to refined estimates of both speed and direction. The resulting data confirmed a hyperbolic trajectory, indicating that 3I/Atlas was traveling faster than the escape velocity of the solar system at its distance. This fact, while scientifically notable, was presented without sensationalism, a simple conclusion drawn from careful measurement. The object's motion was monitored continuously, with each observatory contributing to a shared record. Differences in instruments, atmospheric conditions, and observational methods were accounted for through calibration and correction procedures. Each calculation and adjustment was meticulously documented, ensuring that all results could be independently verified. This systematic approach reflected the disciplined nature of astronomical observation, emphasizing clarity and reliability over speed or spectacle. Mathematical models played a significant role. Orbital simulations incorporated not only the gravitational influence of the Sun and planets but also perturbations from minor bodies and the collective mass of the asteroid belt. These computations required iterative adjustments, with each new set of observations informing subsequent predictions. The process was deliberately slow, favoring precision over immediacy. By continually refining the model, astronomers ensured that the calculated trajectory remained accurate as the object progressed through the inner solar system. The study of velocity also included analysis of the object's changing distance from the Sun and Earth. As 3I/Atlas moved along its hyperbolic path, apparent speed varied due to perspective, requiring careful correction. Astronomers applied trigonometric and geometric methods to account for this effect, producing consistent and reliable measurements. Each night's data contributed incrementally to the overall understanding, a steady progression toward certainty rather than a dramatic revelation. Collaboration among international teams was essential. Observatories in the northern and southern hemispheres provided complementary data, ensuring near-continuous coverage. Time zone differences were accounted for, allowing for coordinated observations and immediate sharing of results. This global network demonstrated the collective patience and attention to detail required for precise orbital determination. Graphical representations of the trajectory were generated as part of the analysis. While these diagrams could suggest movement at a glance, they were intended primarily for verification and comparison rather than dramatic presentation. Each plotted point represented an observation, carefully checked for accuracy, and connected with a smooth curve illustrating the calculated path. These visual aids served as a reference, reinforcing the accuracy of mathematical models and supporting further observational planning. Velocity and trajectory calculations were repeated over several weeks, with new observations integrated into the models each night. Minor adjustments were made as errors or uncertainties were identified, illustrating the iterative nature of scientific measurement. By the end of this period, astronomers possessed a comprehensive understanding of the object's motion, including speed, direction, and predicted passage through the solar system. Each refinement was a product of careful observation, deliberate calculation, and rigorous verification, exemplifying the calm, methodical approach that characterizes professional astronomy. The careful tracking of 3I/Atlas demonstrated the importance of patience in understanding celestial phenomena. Rather than rushing to conclusions, astronomers allowed data to accumulate, adjusting predictions as evidence dictated. The result was a detailed, precise, and reliable account of the object's trajectory, forming the foundation for subsequent study. Observers continued to record positions, calculate velocities, and refine models, all while maintaining a neutral, objective perspective. This steady accumulation of knowledge exemplifies the quiet rigor and attentive focus that underpins astronomical discovery. Observing composition, dust, ice, and light once the motion and trajectory of 3I/Atlas were carefully determined, attention turned to understanding the object itself, its composition, structure, and the light it reflected. Astronomers relied primarily on photometric observations, measuring the intensity and variation of light over time. These measurements, taken at regular intervals, provided insight into surface properties, rotational behavior, and the presence of any coma, the diffuse envelope of gas and dust that often surrounds comets. The brightness of 3I/Atlas was recorded across different wavelengths, ranging from visible light to near-infrared. Each wavelength revealed different characteristics. Visible light indicated general reflectivity, or albedo, while infrared measurements offered clues about surface temperature and material composition. The object's apparent dimming or brightening, noted over successive nights, suggested slow rotational movement, though without rapid fluctuations. Such careful observation allowed scientists to make inferences without the need for dramatic or speculative statements. Spectroscopy, the study of light spectra, provided a second method for understanding composition. Light reflected or emitted by the object passed through spectrographs, instruments that disperse it into constituent wavelengths. Specific absorption or emission lines in the spectrum revealed the presence of particular molecules or elements, such as water ice, carbon compounds, or silicates. The resulting data offered a neutral, factual picture of 3I/Atlas as a small, cold, primarily icy body, with trace amounts of dust and other materials. These findings were recorded meticulously, with each spectrum carefully labeled, calibrated, and archived. Observations were conducted under consistent conditions to minimize error. Atmospheric clarity, telescope calibration, and detector sensitivity were routinely verified. Multiple telescopes, sometimes located in different countries, recorded simultaneous measurements to confirm results. Each site followed standardized procedures, ensuring that all data could be compared reliably. The slow, methodical repetition of these measurements reinforced the accuracy of the conclusions drawn about the object's composition. The surface of 3I/Atlas appeared largely inactive. Unlike some comets within the solar system, it did not display dramatic jets of gas or conspicuous dust tails. Instead, any emissions were subtle, detectable only through precise instrumentation. Astronomers recorded the gradual increase in brightness as the object approached the sun, a result of gentle sublimation of surface ices rather than explosive outgassing. The observation emphasized calm, measurable processes rather than spectacular displays. Rotational periods were inferred from the cyclical variations in brightness, known as light curves. These curves showed slow, regular oscillations, indicating that the object rotated over the course of several hours. Each cycle was analyzed using Fourier methods to extract consistent patterns, enabling a confident estimate of the rotation rate. The process was deliberate and precise, reflecting the patient attention required in observational astronomy. The density of dust and ice was also estimated using models of reflected light and thermal emission. By comparing observed brightness and heat radiation with theoretical predictions for bodies of different sizes and compositions, astronomers could determine approximate proportions of material types. The results indicated a predominantly icy nucleus with minor dust content, a composition consistent with expectations for interstellar objects passing through the solar system. The color of the object, as determined by photometry, suggested a slightly reddish hue, similar to other small bodies originating from the outer reaches of stellar systems. This characteristic, while subtle, was documented for completeness, providing a reference point for future comparisons with other interstellar visitors. The tone of reporting remained neutral, emphasizing precise measurements rather than interpretive speculation. Each observation was cross-checked for consistency. Measurements from different telescopes, taken under varying atmospheric conditions, were compared and averaged to reduce uncertainty. Minor discrepancies were carefully examined, corrected, and annotated. The goal was not to generate excitement or narrative tension, but to build an accurate, repeatable record of 3I/Atlas's physical characteristics. Astronomers also considered the object's reflectivity relative to its orientation toward the sun phase angle corrections, accounting for the geometry of illumination and observation, were applied systematically. These corrections allowed for a more accurate assessment of inherent brightness, independent of perspective, distance, or angle of incidence. The process was slow, meticulous, and essential for the creation of reliable datasets. Over time, the growing collection of photometric, spectroscopic, and thermal data painted a consistent picture. 3I/Atlas was a small, icy object with a gentle, slow rotation, minor dust content, and no signs of dramatic activity. Each night of observation contributed incrementally to this understanding, demonstrating the quiet accumulation of knowledge characteristic of professional astronomy. The careful study of light, color, and composition emphasized patient, observational patience. Observers recorded their findings in detail, documenting methods, calibrations, and conditions. Results were shared within the scientific community, allowing for confirmation and independent analysis. Every measurement contributed to a comprehensive, measured, and factual portrayal of the object, aligning with the objective and calm tone suitable for a sleep-oriented documentary. Tracking motion, calculating the path through space. Once the composition and brightness of 3I/Atlas were reasonably understood, astronomers focused again on its trajectory. Determining the precise path of any object moving through space requires repeated measurements over time. Observers recorded positions against the background stars, noting the exact time, coordinates, and telescope used. These data points were later combined to calculate the object's orbit, or in the case of interstellar objects, its hyperbolic trajectory. In the case of 3I/Atlas, the object followed a path that was unmistakably unbound to the sun. Unlike the familiar elliptical orbits of planets or most comets, it did not return periodically. Calculations of its speed and direction indicated that it was moving faster than typical solar system objects and on a path that would eventually carry it beyond the gravitational influence of the sun. Observers noted this fact calmly, recording numerical values without embellishment or dramatic interpretation. The process of plotting the trajectory relied on classical celestial mechanics. Observers used the measured positions to derive velocity vectors, then applied gravitational equations to model how the object would interact with the sun and nearby planets. Each step of the calculation was carefully documented. Observers recalculated repeatedly, incorporating new data to reduce uncertainty. This iterative approach, while slow and methodical, ensured accuracy. Observations were not limited to a single site. Multiple observatories, sometimes spanning continents, contributed measurements. Coordinating these observations required careful timekeeping, including adjustments for local time zones, telescope clock errors, and atmospheric refraction. Each correction was small but significant, allowing astronomers to refine their predictions with precision. The resulting trajectory maps showed the object's approach from outside the plane of the solar system. Its path through the inner solar system was gradual, without abrupt changes, and its closest approach was recorded as a specific distance in astronomical units. Observers calculated the expected future positions for weeks and months, ensuring that telescopes could continue to track the object as it moved outward again. The velocity of 3I/Atlas was also carefully examined. By comparing positions over time, astronomers derived a speed relative to the Sun that was higher than typical for comets or asteroids bound to the solar system. This velocity reinforced its classification as an interstellar object and provided a benchmark for comparison with future discoveries. The calculations were precise and neutral, intended for record-keeping rather than sensational reporting. Predictions of motion included uncertainties, expressed as small ranges in position or velocity. These uncertainties decreased over time as more observations were added. The gradual reduction of uncertainty exemplified the steady accumulation of knowledge characteristic of scientific study. Even minor deviations were recorded, ensuring a complete, factual account of the object's behavior. The calculated orbit also allowed astronomers to estimate the time the object had been in interstellar space before its encounter with the Sun. While exact origins remained unknown, the orbital data suggested a long journey through the space between stars. Observers noted the extended distance traveled without adding conjecture or narrative tension. The focus remained on measurable facts. In addition to orbital calculations, astronomers considered external influences on the trajectory. Gravitational effects of planets, particularly Jupiter and Saturn, were assessed to confirm that their influence on 3I/Atlas was minimal, given its high velocity. Solar radiation pressure and the slight outgassing of the object were included in models but contributed only minor adjustments. Each factor was accounted for with careful arithmetic, ensuring a complete understanding of the forces at play. All calculations and observations were logged in standardized formats. Data tables, graphs, and charts were prepared for review by colleagues and future reference. The emphasis on clear, accurate, and reproducible work reflected the overarching principle of calm, objective documentation. Even as the object moved through space at high speed, the process of observation remained slow, deliberate, and precise. Through these methods, astronomers achieved a comprehensive understanding of 3I/Atlas's motion. They knew where it had been, how it moved through the solar system, and where it would go next. The study exemplified patience, rigor, and consistent attention to detail, demonstrating the scientific commitment to knowledge rather than spectacle. The tracking of 3I/Atlas illustrated the quiet beauty of astronomy. The ability to follow a small, distant object across vast stretches of space with nothing more than careful measurement, calculation, and observation. Each step, though methodical and understated, contributed to a complete picture of the object's passage through the solar system, providing both a record of discovery and a model for understanding future interstellar visitors. The slow unfolding of early observations and confirmations as the observations of 3I/Atlas continued, astronomers moved gradually from initial detection to confirmation and cataloging. The early days were characterized by meticulous cross-checking, repeated imaging, and careful note-taking. Each new measurement was compared with previous ones to ensure consistency, reducing the possibility of error. The pace was deliberate, with no rush to announce findings before they could be verified. Confirmation of an interstellar origin involved several steps. Observers first ensured that the object's speed and trajectory could not be explained by any known solar system orbit. Repeated measurements confirmed its hyperbolic path and its approach and departure from the Sun at velocities higher than the escape speed of the solar system. Only after these calculations were verified did the classification as an interstellar object become broadly accepted. Parallel to orbital analysis, the object's brightness and appearance were monitored over time. Observers recorded subtle changes in magnitude, noting any diffuse features, such as a faint coma or tail formation. The appearance of 3I/Atlas remained relatively consistent, with small variations interpreted cautiously. Changes were documented numerically, rather than described with subjective adjectives, maintaining the calm and neutral tone of the study. The object's interstellar classification was strengthened by the lack of correlation with known cometary populations. Databases of past comets and asteroids were consulted to ensure the object had not been previously recorded. Observers carefully compared orbital elements, ensuring that 3I/Atlas was unique. Each comparison added confidence, reinforcing the object's status without creating urgency or excitement in the reporting. Communication among the astronomical community was measured and formal. Observatories shared data through structured channels, often using electronic circulars or secure databases. Each contribution included precise timing, measurement uncertainty, and instrument specifications. The coordination allowed scientists around the world to maintain an accurate, up-to-date record of the object's motion and characteristics. During this period, early publications emerged, but their style reflected the same calm objectivity as the observations themselves. Papers outlined methodology, data collection, calculations, and results without narrative embellishment. The focus remained on clarity and reproducibility, ensuring that future astronomers could review, verify, or build upon the findings. Despite the absence of dramatic events, the confirmation process was meticulous. Each observation contributed incrementally to the understanding of the object's path, size, and composition. Observers noted when imaging conditions, such as weather or atmospheric turbulence, influenced measurements and corrected accordingly. This attention to detail exemplified the patient accumulation of knowledge. In addition to observational confirmation, computational models were applied to simulate the trajectory and interaction of 3I/Atlas with solar system bodies. Small variations in gravity, position, or velocity were incorporated to produce refined predictions. These simulations were repeated multiple times, ensuring that any discrepancies could be identified and explained. The models reinforced observational findings, demonstrating the object's consistent behavior across both measurement and theory. The object's interstellar origin also prompted careful consideration of potential sources. While exact provenance could not be determined, astronomers examined nearby star systems and the broader galactic environment. Estimates of travel time and direction were made cautiously, with attention to mathematical plausibility rather than narrative speculation. The approach exemplified a focus on measured fact, rather than conjecture or imaginative storytelling. Throughout this period, every step unfolded slowly, as intended. Observers took time to verify data, check calculations, and consider alternative explanations. Each minor adjustment, whether in velocity, magnitude, or position, was logged methodically. The process reflected not urgency, but steady diligence, a hallmark of calm scientific practice. By the conclusion of early observations, 3I/Atlas had been recorded, tracked, and classified in a manner that would serve as a reference for future interstellar objects. Its passage through the solar system was understood in precise detail, not through sensational headlines, but through quiet, incremental accumulation of knowledge. Each small piece of data contributed to the larger picture, providing a foundation for long-term study. This stage illustrated the patient rhythm of astronomy. The journey from first sighting to confirmed classification is not rapid. It relies on repeated measurement, cross-validation, and the careful synthesis of multiple data sources. The process exemplifies the meticulous nature of observational science. Slow, deliberate, and exacting. In reflecting on these early confirmations, one observes the steady interplay of observation, measurement, and calculation. Every night spent recording positions, every spreadsheet of brightness readings, every calculation of velocity contributes quietly to understanding. There is no rush, no dramatic climax, only the careful unfolding of facts. Through the calm, consistent documentation of 3I/Atlas, astronomers created a record that is both enduring and reproducible. The object's journey through the solar system is now a matter of precise record, a slow story told in numbers and coordinates rather than dramatic narrative. And while the wider universe continues in silent motion, the early observation period of 3I/Atlas remains a model of patient scientific inquiry, a reminder that understanding often comes not through spectacle, but through consistent, careful attention over time. Once 3I/Atlas had been confirmed as an interstellar visitor, astronomers turned their attention to tracking its motion across the sky with methodical care. Observations were made nightly, often under varying atmospheric conditions, with each measurement meticulously noted. Telescopes at multiple observatories recorded precise coordinates, using consistent time standards to ensure that data from different locations could be accurately combined. The object's apparent motion against the background stars was slow, measured in degrees per day, yet noticeable when data points were plotted over consecutive nights. This allowed astronomers to refine their orbital calculations, reducing uncertainty in its predicted path. Each observation was accompanied by details of exposure time, filter type, and sensor calibration. By maintaining consistent methodology, observers ensured that results from disparate instruments could be synthesized into a coherent record. Tracking 3I/Atlas required patience. Weather conditions often delayed imaging sessions, and faint brightness levels meant longer exposures were necessary. Observers documented the effects of atmospheric turbulence, moonlight, and instrumental noise. Adjustments were made carefully, often reprocessing earlier images to maintain a consistent dataset. No single measurement was relied upon in isolation. Each was corroborated with preceding and subsequent readings to reduce potential error. Photometric measurements were collected to monitor changes in apparent brightness. Observers recorded magnitude values across different wavelengths, noting any slight variations. Even subtle changes were logged with precision, allowing the compilation of a slow-moving, detailed record. Observers interpreted these variations with neutrality, refraining from dramatic speculation. Small fluctuations were understood in context. Minor rotational differences, observational limitations, or naturally occurring material shedding were considered plausible explanations. Astrometry, the precise measurement of position, was equally important. Each night's observation contributed to the calculation of its hyperbolic trajectory. The object's departure from the solar system was gradual, its motion predictable within narrow margins. Astronomers compared its trajectory to those of previously recorded interstellar objects, noting similarities and differences. These comparisons were statistical and quantitative, rather than narrative. While amateur astronomers occasionally contributed observations, professional teams ensured that data met strict standards. Observational protocols required multiple measurements and repeated imaging sequences. These procedures minimized random error and provided redundancy. Data were logged in standardized formats, allowing for verification and cross-referencing. The repeated observations also revealed subtle details about 3I/Atlas's rotation. Light curve analysis indicated gradual changes in reflected light, suggesting an irregular shape. These measurements were taken slowly, over multiple nights, to avoid misinterpretation. The results were presented in tables and graphs, illustrating consistent changes over time without relying on dramatic language. As tracking continued, observatories coordinated schedules to follow the object as it moved across hemispheres. Northern and southern observatories shared data, ensuring continuous monitoring. By combining datasets, astronomers maintained near-continuous coverage despite the Earth's rotation and varying weather conditions. This collaboration exemplified the careful, deliberate rhythm of scientific observation. Throughout these processes, communication was calm and precise. Updates were shared via electronic circulars, listing coordinates, magnitudes, and observational conditions. Each contribution was factual, avoiding narrative embellishment. Observers noted uncertainties explicitly, allowing for transparent interpretation by other teams. In essence, the monitoring of 3I/Atlas was a slow, methodical endeavor. Each night, each exposure, each calculation added a small, reliable piece to a larger puzzle. There was no urgency, only the careful accumulation of knowledge. Observers documented the object's journey with patience and precision, creating a comprehensive record that could be referenced for years to come. Through these disciplined practices, 3I/Atlas became not merely a point of light, but a well-understood interstellar visitor. Its motion across the sky was charted with clarity, its characteristics recorded with subtlety. The process exemplified the quiet diligence of astronomy, demonstrating that the understanding of celestial objects often emerges through careful, repetitive observation rather than dramatic revelation. Instruments and techniques. How 3I/Atlas was measured. The observation of 3I/Atlas relied on a range of telescopes and detectors, each contributing to a comprehensive understanding of the object. Optical telescopes, equipped with sensitive charge-coupled devices, recorded images across various filters to capture reflected sunlight at different wavelengths. These images were analyzed systematically, ensuring that each pixel's data could be compared night after night. Observers took care to maintain uniform exposure times and consistent instrument settings, reducing variability in measurements. In addition to optical instruments, some observatories employed near-infrared detectors. The infrared readings complemented the optical data, revealing subtle variations in temperature and composition. Observers carefully calibrated their instruments to account for atmospheric absorption and instrumental noise. Every adjustment was documented, providing a reliable record of the observational process. Photometry, the measurement of brightness, was conducted using standardized protocols. Magnitude values were calculated relative to reference stars in each frame. By maintaining consistent reference points, astronomers could track changes in 3I/Atlas's brightness over time. These fluctuations were minor, reflecting slight differences in orientation or surface features, rather than sudden outbursts or unexpected events. The data were recorded in tables and spreadsheets, forming a slow-moving timeline of the comet's luminous profile. Astrometry, or the precise determination of position, was equally structured. Observers used multiple reference stars to triangulate the object's location with exacting accuracy. Coordinates were recorded in right ascension and declination, following conventions that allowed seamless comparison across observatories. Each night's observations were combined with previous measurements, refining calculations of its hyperbolic trajectory and predicting its future path with increasing certainty. Telescopes were sometimes operated remotely, allowing observatories in different countries to contribute to the dataset. Observers coordinated schedules to ensure continuous coverage, compensating for time zone differences and local weather conditions. The distributed nature of the work meant that data could be collected without interruption, creating a near-constant record of 3I/Atlas's movement. Observational techniques were selected for reliability rather than speed or spectacle. Longer exposure times allowed faint details to emerge, while repeated measurements reduced random errors. Multiple images were stacked and averaged to enhance signal quality, providing a stable, noise-reduced representation of the object. Observers maintained meticulous notes on conditions such as sky clarity, humidity, and seeing, all of which could subtly influence results. Some observatories also employed spectrographs, instruments that disperse light into its constituent colors. Spectroscopy revealed chemical signatures in the comet's coma and tail, indicating the presence of simple molecules like water, carbon dioxide, and other volatiles. These readings were analyzed slowly, with spectra compared against reference libraries to avoid misinterpretation. Each finding was recorded with careful notation of instrument settings, date, and observational conditions. Data management played a critical role in the process. Observers organized files systematically, labeling each image and measurement according to standardized naming conventions. This allowed researchers to retrieve and cross-check information efficiently. Backup copies were maintained to prevent loss, ensuring the continuity of the dataset over weeks and months. Collaboration extended beyond data collection. Analysts regularly reviewed measurements for consistency, verifying that results from different instruments aligned within expected margins of error. Discrepancies were investigated methodically, often requiring reanalysis or recalibration rather than assumptions about the object's behavior. The process emphasized patience and precision over rapid conclusions. Throughout, communication between teams remained neutral and factual. Circulars and electronic bulletins provided updates on position, brightness, and observational conditions. These reports avoided narrative embellishments, focusing on data, measurements, and the careful interpretation of results. The cumulative effect of these instruments and techniques was the creation of a detailed, reliable record of 3I/Atlas's presence in the sky. Every measurement, no matter how minor, contributed to the larger understanding of the object. Observers relied on consistency, repetition, and methodical procedures to transform a faint point of light into a well-characterized interstellar visitor. By emphasizing meticulous observation over dramatic presentation, astronomers ensured that the story of 3I/Atlas was rooted in precise data rather than speculation. The process illustrated the deliberate rhythm of scientific inquiry, where slow accumulation of information gradually yields clarity. Each night of measurement, each calibration, each analysis reinforced the overall picture, providing a foundation for subsequent studies of interstellar objects. Comets, asteroids, and interstellar visitors. Defining 3I/Atlas. To understand 3I/Atlas, it is helpful to place it within the broader context of small bodies in our solar system and beyond. Objects orbiting the Sun are generally classified as either asteroids or comets, each distinguished by composition, behavior, and orbital characteristics. Asteroids are primarily rocky or metallic bodies, often concentrated in the asteroid belt between Mars and Jupiter, though they can be found throughout the solar system. Their surfaces are relatively inert, and their appearance is often steady over time. Comets, by contrast, are composed largely of ice, dust, and volatile compounds. As they approach the Sun, sublimation causes gases to escape, forming a coma and occasionally a visible tail. These features give comets their characteristic appearance and provide insights into their composition. Observation of comets requires careful timing, as brightness and visibility can change gradually over weeks or months, rather than abruptly. 3I/Atlas does not fit neatly into either traditional category. Its hyperbolic trajectory, an orbit that is not bound to the Sun, distinguishes it as an interstellar object. Unlike comets or asteroids that circulate repeatedly around the Sun, 3I/Atlas entered the solar system from interstellar space and will eventually leave, continuing its journey through the galaxy. This distinction is purely orbital. It is defined by its motion rather than by any dramatic physical characteristic. Despite the unusual origin, 3I/Atlas shares some characteristics with comets. Observations revealed a small coma, suggesting that the object contains volatile materials capable of sublimating in sunlight. The effect, however, is subtle. Its tail is not the dramatic plume often associated with comets seen from Earth, but rather a faint trail detectable only through careful measurement. This measured, understated presence exemplifies the difference between scientific observation and popular perception. The data provide information rather than spectacle. The process of classification is deliberate. Astronomers rely on precise measurements of orbit, speed, and trajectory. When an object's orbital eccentricity exceeds 1, it is defined as hyperbolic, indicating that it is not gravitationally bound to the Sunday. 3I/Atlas's trajectory met this criterion, leading to its designation as an interstellar object. The designation does not imply mystery or danger, only a technical acknowledgement of its path. Comparisons with previous interstellar objects are also made methodically. 1I/Oumuamua, the first confirmed interstellar object, exhibited an elongated shape and subtle acceleration, raising questions about its composition. 3I/Atlas, while less dramatic in appearance, offered another data point for studying bodies from beyond the solar system. Observers treated each characteristic as a measurable property, recording shape, brightness, and trajectory without drawing speculative conclusions. Asteroids, comets, and interstellar objects are cataloged systematically. Each type has a naming convention that conveys information about discovery, orbital characteristics, and survey program. 3I/Atlas, as an interstellar comet, fits within this structured system, demonstrating the scientific commitment to order rather than narrative embellishment. Observers and catalogers rely on consistency in terminology and documentation, ensuring that each object can be referenced unambiguously in research publications and databases. The distinction between types of objects also has practical implications. Understanding whether a body is a comet or asteroid informs observational priorities. Comets with active volatiles may require photometric monitoring to track changes in brightness and tail development, whereas asteroids may only need periodic astrometric checks to confirm position. Interstellar objects, transient by nature, demand a combination of both approaches: precise positional tracking and careful assessment of any observable activity. 3I/Atlas serves as a case study in categorization. Its orbit, modest activity, and detection through survey programs exemplify the measured approach astronomers take. Each observation contributes to a comprehensive profile, forming a picture of an object that is both ordinary in its measured behavior and extraordinary in origin. The calm, structured methodology ensures that the focus remains on verifiable properties rather than speculation or sensationalism. By emphasizing the subtle distinctions between asteroids, comets, and interstellar objects, astronomers can maintain a clear framework for understanding celestial bodies. 3I/Atlas's classification illustrates the careful interplay between observation, measurement, and systematic categorization. The result is a record that is informative and reliable, offering insight into both our solar system and the wider galactic environment through calm, precise description. The first sightings of 3I/Atlas. The initial detection of 3I/Atlas occurred during the routine scanning of the night sky, an operation that relies on automated telescopes and continuous observation schedules. The Atlas survey, designed to identify transient objects such as asteroids or comets that might pose a potential impact risk to Earth, captures images of the sky at regular intervals. Each exposure is carefully cataloged and analyzed by software designed to detect movement or changes in brightness. The process is deliberate, with a focus on accuracy and completeness rather than speed or dramatization. On a quiet night, the telescope recorded a small, faint object moving against the fixed backdrop of stars. Its motion was initially subtle, only noticeable because the software compared consecutive images and flagged deviations. The object did not immediately stand out as extraordinary. It appeared as a small point of light, similar to numerous other minor objects routinely tracked in the survey. At this stage, the detection was an instance of systematic observation rather than a discovery heralded by spectacle. Astronomers examined the object's movement across multiple images, calculating preliminary orbital parameters. The trajectory suggested that it was not bound in a circular orbit around the Sun, a detail that would later become significant. Initially, the object was catalogued under the standard nomenclature for new discoveries, following established conventions. Each entry in the catalog includes date, coordinates, apparent magnitude, and motion characteristics. This meticulous documentation ensures that every object can be reliably referenced in future studies. Following the initial detection, additional observations were scheduled to confirm the object's path and characteristics. Ground-based telescopes around the world were enlisted, each contributing measurements that refined the understanding of its motion. Observers noted that its speed and trajectory were unusual compared to typical asteroids and comets. While the observation itself was uneventful, the accumulation of precise data enabled astronomers to determine that the object's orbit was hyperbolic, confirming that it originated from outside the solar system. The subsequent classification as an interstellar object was based purely on measured motion. The hyperbolic orbit indicated that the object was not gravitationally bound to the Sun, meaning it was passing through the solar system for the first time. The designation 3I/Atlas reflects both its interstellar nature and the survey responsible for its detection. The name follows the convention established by the International Astronomical Union, ensuring consistency across scientific records. The cataloging process is deliberate and methodical, emphasizing clarity and neutrality. Observations were not limited to position alone. Astronomers also measured brightness and searched for signs of activity, such as a faint coma or tail. 3I/Atlas exhibited subtle indications of volatile material, though the effects were minimal. This information was recorded alongside orbital data, forming a comprehensive profile of the object. At every stage, the emphasis was on objective measurement rather than conjecture. Each value, speed, trajectory, apparent magnitude, was verified against previous observations, ensuring that conclusions were based on repeatable, documented evidence. The careful process of detection and confirmation highlights the systematic approach astronomers use when monitoring the sky. A small point of light becomes an interstellar visitor not through sudden revelation, but through repeated, consistent measurement. The identification of 3I/Atlas is a demonstration of observational diligence. It is the result of structured programs, precise instrumentation, and methodical data analysis. Each observation builds incrementally on the previous, creating a steady, unhurried understanding of the object. The historical context is also relevant. The discovery of 3I/Atlas followed the earlier detection of 1I/Oumuamua, which provided a template for recognizing interstellar bodies. Lessons learned from previous cases informed the monitoring and verification process. Observers knew what to look for: subtle movement across images, deviations from bound orbits, and any indications of outgassing. This prior knowledge contributed to a calm, measured approach, where each step was deliberate and methodical, avoiding speculative conclusions until sufficient evidence was collected. By the conclusion of the early observation period, 3I/Atlas had been reliably tracked and catalogued. Its interstellar origin was established through orbital calculations, and its faint activity suggested a composition that resembled comets within the solar system. The data were shared within the scientific community, allowing for independent verification and further study. The process exemplifies the collaborative nature of astronomy, where observations are corroborated and recorded in a manner that prioritizes accuracy and consistency. The story of 3I/Atlas's discovery is, in essence, a story of quiet diligence. It illustrates how a small, faint object, initially unremarkable in appearance, can be recognized as extraordinary through careful observation and measurement. The emphasis remains on data, precision, and systematic methodology. There is no urgency, no dramatic revelation. Rather, there is a calm unfolding of understanding, each step documented with care, forming a foundation for continued study. The slow unfolding of early observations and confirmations after the initial sighting of 3I/Atlas, the process of understanding its nature proceeded deliberately. Observers relied on repeated measurements taken over multiple nights, each one contributing incremental clarity to the object's trajectory and physical characteristics. The pace was methodical, dictated by the need for accuracy rather than urgency. Astronomers recorded each position with precise timestamps, comparing data across observatories. Even minor discrepancies were noted and analyzed, as these could refine orbital calculations or reveal subtle effects such as outgassing or rotational behavior. The confirmation of 3I/Atlas as an interstellar object required collaborative verification. Observatories across different hemispheres contributed observations to ensure that the object's motion was not misinterpreted due to parallax or observational error. The process involved cross-checking data points, recalculating orbits, and ensuring that results were reproducible. Each step of confirmation followed a steady, predictable rhythm: measure, compare, record, and repeat. There was no rush to declare the discovery to the public, no sensational announcement, but rather a careful accumulation of facts that would withstand scrutiny. Photometric analysis played a crucial role in these early observations. By measuring the brightness of 3I/Atlas across different wavelengths, astronomers could infer aspects of its composition and surface properties. Slight variations in brightness hinted at rotation, while consistent faint outgassing suggested the presence of volatile materials, though in modest quantities. Each observation was meticulously catalogued, contributing to a slow but continuous understanding of the object's physical characteristics. The approach was neutral and objective, focusing on data rather than speculation. As the object continued along its hyperbolic path, astronomers monitored its motion relative to background stars. Small adjustments to orbital calculations were made as more data became available, reducing uncertainties and improving predictions of its position. This iterative process exemplifies the careful, measured approach that defines observational astronomy. Each new observation was incorporated into a larger framework, gradually painting a precise, though unhurried, picture of the object's journey through the solar system. The timeline of confirmations reflects this calm diligence. Initial observations suggested an unusual trajectory. Subsequent nights provided independent verification. As orbital elements were refined, the hyperbolic nature of 3I/Atlas became clear. Its velocity exceeded what would be expected for objects bound by the sun's gravity, indicating that it was truly an interstellar visitor. Throughout, the emphasis remained on precision and clarity rather than narrative excitement. Data were compiled into tables and charts, documenting each measurement and associated uncertainty. The communication of these early results also followed a restrained process. Astronomers shared preliminary data through internal networks and circulars, allowing peers to review and corroborate findings. This peer verification ensured that the classification of 3I/Atlas as interstellar was supported by independent measurements. Observatories continued to gather information on brightness, position, and potential activity, creating a cumulative record that could be referenced in future studies. While public awareness would eventually grow, the early work was characterized by quiet diligence. There was no rush to speculate about origin or implications. Instead, the object was treated as a subject for careful study. Its discovery demonstrated the effectiveness of systematic sky surveys and highlighted the importance of incremental, reproducible observations. Each data point, each measurement, contributed to a comprehensive understanding of the object's motion and composition. Even as telescopes continued to monitor 3I/Atlas, the process maintained its steady cadence. Observers adjusted exposure times and filters to optimize measurements, all the while adhering to the calm routines established by the Atlas survey. The careful attention to detail ensured that every piece of information was reliable, forming a foundation for continued analysis and comparison with future interstellar objects. By the conclusion of this early observation period, 3I/Atlas had been well characterized. Its trajectory was precisely known, its hyperbolic orbit confirmed, and its faint physical activity documented. The slow unfolding of observations demonstrated the value of patience and meticulous methodology. What had begun as a faint, barely noticeable point of light had become a well-understood interstellar visitor, mapped and measured with calm, deliberate attention. The story of these early observations is, in itself, unhurried and reassuring. It is a narrative of methodical work, careful verification, and the quiet accumulation of knowledge. There is no dramatic tension, no urgent climax, only the steady development of understanding. For those who observe from afar, 3I/Atlas serves as an example of how human curiosity, combined with structured observation, can transform a fleeting moment into a lasting record of discovery. In the end, the early monitoring of 3I/Atlas illustrates a fundamental principle of astronomy. Meaningful understanding arises not from spectacle, but from repeated, careful measurement and verification. Each observation contributes a small piece to a larger puzzle, and through patient study, the nature of even a distant interstellar visitor can be understood. The calm, consistent methods employed in these early stages provide a foundation for all subsequent study, ensuring that the information collected is reliable, precise, and enduring. The story of 3I/Atlas unfolds not as a tale of sudden discovery or dramatic revelation, but as a quiet testament to the measured, patient work of those who observe the heavens. From the careful assignment of its name, through the systematic scanning of the skies, to the gradual confirmation of its interstellar nature, every step was marked by calm precision. The object itself, a solitary traveler from beyond our solar system, moved silently against the backdrop of countless stars, unaware of the human attention it would quietly command. Through methodical observations and repeated verification, astronomers transformed a faint, almost unnoticed point of light into a well-understood visitor. Each measurement, each orbital calculation, each faint indication of outgassing contributed to a cumulative understanding that required neither urgency nor spectacle. In this deliberate accumulation of knowledge, there is a sense of reassurance. The universe can be explored with patience, and understanding can emerge from consistent attention to detail. The story of 3I/Atlas is also a story of perspective. It reminds us that the cosmos is vast, and that our place within it can be observed with calm curiosity rather than anxiety. The interstellar object, traveling silently across unimaginable distances, provides a gentle reminder of the quiet rhythms that govern celestial motion, and of the steady human effort required to comprehend it. Ultimately, 3I/Atlas is more than a name or a catalog entry. It is a symbol of careful observation, of meticulous verification, and of the quiet ways in which knowledge accumulates over time. The object will continue on its journey, moving beyond our solar system, while the records of its passage remain as a subtle, enduring testament to human patience, curiosity, and the slow unfolding of understanding. And so, in observing 3I/Atlas, we witness not only the movement of a solitary visitor through the sky, but also the calm diligence of those who watch, record, and interpret the universe with steady, unhurried care. It is a reminder that even in the vastness and apparent indifference of space, attentive observation can transform fleeting glimpses into lasting insight, offering a gentle reassurance to those who seek knowledge with patience and quiet curiosity. And so, as 3I/Atlas drifts quietly beyond our sight, we too can rest, knowing that the universe moves with calm patience, and that all things unfold in their own gentle time.